Okay, we should start. So, session 2 talks. The first one is given by Fogler. It's a San Diego, and it will be about Coulomb gap in the Neuron quantity systems.
So thanks for the invitation. So it's very nice to meet everybody again. So this is a talk. Actually, I gave this talk 14 years ago. I was coming here. I was thinking, what did I do which relates to long-range interactions and disorder, and I found this unpublished paper. So I was hoping to publish it before coming here, but I still haven't. So so I guess it's still kind of work in progress. So it's about Coulomb gap in 1D. So I guess in this audience, don't need to explain what Coulomb gap is. So this is just a picture of a model where it can appear. You have disordered sites. So energies, epsilon i's, positioned randomly. We assume that everything's classical, so there's Coulomb interaction to point-like charges. And because on-screen Coulomb interactions, there will be correlations between occupations of those levels. And so as we know, the famous, the one-line derivation from this famous paper gives this result. So let me explain it again, because that's more or less also only one of the equations. So when you move electron from occupied to empty space, so naively you would say that energy of that process is a difference in the site energies, but actually you have to include the change in this energies because the charges are rearranged. So this is excitonic shift, e squared over distance. So the whole thing, the system will remain stable if this energy changes positive, non-negative, which requires the sites of flow energy to be far away, so or sparse. And this is why the density of states must be depleted. So this argument gives the Coulomb gap, so-called Coulomb gap. So it's not a gap really, it's like pseudo gap. So the shape. So in all dimensions, density of states goes to 0 at the Fermi energy. But the way how it approaches 0 depends on dimensionality. So in 3D, this argument gives quadratic dependence. So e squared over charge of electron to the 6. In 2D, it's linear, so kind of cusp. So absolute value of epsilon divided by epsilon to charge to the 4th. Okay, and what happens in 1D? So that's more or less the topic of this talk. Okay, so the answer is also known. So a little bit more subtle. So because you see that essentially the power is d minus 1. So if you use d equals to 1, you will get 0. So what is power 0? Sometimes power 0 is a constant, and sometimes power 0, it means you have a logarithm. So here, the answer is it's a logarithm. So this 1 over log suppression with density of states. So this result, I guess, was obtained first by Reich, Efros, but also many other people worked on that. And so the whole, it's not controversial, I don't think. The only thing which is controversial, or I don't know, worth discussion is the coefficient. So the whole thing, that's why Boris will not approve of my talk. I think I tried to discuss with you 14 years ago. We were both at the workshop together.
I was arrogant then.
So the whole thing is about a number, and so what's the big deal? So okay, anyway.
No, I am not.
So this is some experimental data for beryllium film. It shows, I think, well, I think it was a sequence of different films. It's a Butko and company. They were interested in studying metal insulator transition. So you have Coulomb gap if system is an insulator. Okay, so this two-dimensional material has this very beautiful cusp linear Coulomb gap in 2D. I'll show some results, experimental results in 1D. It's less beautiful towards the end of my talk. But I think that's one of the very nice demonstration of Coulomb gap directly in tunneling experiments. If you dop this, I forgot what we did with this film. To make it more metallic, then the gap disappears. But anyway, so this is a red line. It shows up in transport. It shows up in so in tunneling conductance shows up in transport. The famous square root T Hoping formula and many other things, right? So, so one question which was always hard to answer is how to go beyond this simple argument, beyond Efros Chklovskii bound. So it gives basically the upper limit on the Coulomb gap. Okay, so the idea is that here we're using some kind of stability argument, right? We say we're looking for the ground state, and one way to find the ground state is to check that any deviation from that state will cause you extra energy. So you check first order stability criterion by just moving one pair of, just make one electron hole pair, basically excitation. Okay, but what about higher order? So 2 electron hole pairs, 3 electron hole pairs. In principle, you have to check all of them to make sure that it is a ground state. So then if you do it for at like lowest order, it gives you upper bound, not immediately clear set. So is a true density of states given by this power energy to the power d minus 1? It's an overestimation. So this kind of further rearrangements of more like particles involved. It's known in the literature as a polaronic effect. So Efros, Chklovskii, and I guess Mott probably was the first to talk about it for some reason. Mott 1975. So, but definitely Boris and Alexei talked about this, and so the if you like minimize it with respect to all this additional and call this additional energy shift delta E polaronic, so then the true stability should include that as well. And so the question is it big or small? And so this is I guess what is what was believed. I guess the last maybe word on this was in the review, which is again 20 years ago by Efros, published in some book. And his quotation is that we believe this theory for 2D systems is basically complete and correct, but we're not so sure about 3D. And the reason why he wasn't so sure is, basically, whether there is indeed a big parametric difference between the Efros Chklovskii bound and the true density of states. So in 3D, back in the 70s, 80s, they think it was a parametric difference, and then maybe later, not so sure.
The paper of myself, Efros, and Skinner, where we resolve this problem. But it has nothing to do to your.
Okay. So maybe I'm not up to date on this as well. But in 2D, and I guess by extension in 1D, the idea is that this is all you need, but maybe some numerical factor is missing. Okay, so talking about numerics. So of course there's a lot of numerical simulations over the years. So again, I apologize if I didn't keep up with literature. So this is some very large scale simulations by Möbius, I guess, from 2009. He did it in all dimensions using some tricks. You cannot do, of course, the system size rigorously. He used some tricks, but anyway. So this is what he found, that indeed. So like in 3 dimensions, this is this straight line. So you do it log plot to show the power law. So straight line with slope 2 is slightly above the actual numerical data, but only maybe by a factor of less than 2. So maybe there is a factor of 2 difference between the exact and the simple theory. Okay, but my talk is about 1D. So from the same paper, numerical calculations, this is the plots. Okay, and this is what you can compare with. So I said in 1D, the Coulomb gap is logarithmic. So you should do the following. You should not plot 1 over G. G is the density of states. 1 over G versus log of energy, and look for the, again, straight line fit. So to this formula. And so this fit gives 1.95. Well, so depending on disorder, B represents the magnitude of disorder. Okay, so maybe when disorder is very weak, you can see maybe slightly higher slope. Okay, but if disorder is sufficiently strong, with some dimensionless units like 10 or above, all the curves can be fitted to this 1.95 times the logarithm. Okay, so previous years, with less sizes, so this is like 20 million size simulations, but back in 90s or 80s, other groups did simulations, and there's some results from those papers I can tabulate it. So you see that maybe for weak disorder, it's 2.2 or something, but then kind of seems like if you increase the disorder, it approaches this, I don't know, universal limit of 2. Okay, which is, however, different from the predictions of Reich and Efros, Baranowski, Efros, Chklovskii, and there's also some analytical. I'll mention this by Chklovskii, but actually agrees with Voigt and John. So I was so the reason actually I started working on that, I thought I didn't know it was a problem. But back in 2009, there was some experiments on graphene nanoribbons, which showed a gap. And so there was different ideas about source of this gap. So there's edge roughness or something, but I thought maybe it's a Coulomb gap. And so I started digging into that and realized there's some discrepancy in the theory of Coulomb gap. So it would be nice to settle it, especially if there is a belief that the theory is correct and complete. So then why is the discrepancy? And then see what we can do. Okay, so why does Efros say, or other people say, that this argument, which doesn't require any high order excitations, is good enough in 1 dimensions? What you can do is just calculate how many particles can be possibly involved. So this is a calculation of density of states of pairs, electron hole pairs, subject to the perturbation which you put on the charge at some point. So it involves basically some kind of integral over energies and positions. And so what enters is G squared, because you need the 2 particles. So that's the proportion of G squared. And when integrating over space, you get a log, because the distances related to energies is 1 over R, right? In the Coulomb law. And so what you see that then this number, the average number, typical number of pairs, is actually less than 1. So in other words, it doesn't happen. Okay, so typical situation is that you just have 1 stability criterion to worry about. Okay, now why is this problem different in higher dimensions? Because depending how you do it, the number of excitations will go. So like if you do in 2D, you get well, actually I haven't seen this calculation specifically done Boris's and F's papers, but the statement was it's of order 1, but maybe some up to some logarithmic factors. Okay. Okay. So this whole thing, of course, is about logarithms, so maybe it's not so innocent, but still. But in 3D, it's even more subtle. So I think originally, in some early version of their work, this number of excitations was very large, much larger than 1. Later, Efros revised it and using some scaling arguments or some hypothesis, and was kind of unsettled. So that's why 2D and 3D maybe there's still some work to be done, although you said Brian and you and resolved it. But in 1D, seems like it's okay. In 1D, seems like things are simple. So just one stability criterion to worry about. So I want to reformulate it as some kind of thermodynamic problem, and see if I can get some handle on it. So so stability criterion is again is that if you have sites, okay, so my sites, and with some energies, let's call them epsilon prime, epsilon double prime, one above Fermi level, one below Fermi level. So the one below is occupied, the other is empty. So then this situation is allowed, okay, if distance between these two pair of sites is larger than 1 over, or is squared over this energy difference. So I'm going to call it capital R. And so the idea is that, so this kind of, so essentially you have in this energy position diagram, okay, if you put a particle here, then there is this 1 over R, this one, hyperbolic region, okay, which you're not allowed to put sites. So this X is basically like a kind of like excluded region or hardcore potential for some fictitious particles. So you can think now about, you know, as I said, hardcore potential, so which is equal to 0 outside of this distance and equals to infinity inside of the distance. Okay, and you can say my density of states, G is a function of energy, can be written as a statistical weight. Okay, so I write it like as a Boltzmann or Gibbs factor with a total potential, which is a hardcore, sum of the hardcore potential between pairs of sides. So if this potential takes only two values, 0, infinity. So if it's 0, that's allowed. Otherwise, you have to exclude it. So then I have this picture, then in this kind of analogy of a thermodynamic system. So I introduce some. I'm interested, of course, in 0 temperature, although you can talk about Coulomb gap at finite temperature as well. But I introduce some fictitious temperature and fictitious particles, which live on this line. This line, I call it X here, but in fact, this is energy. So and these particles come in different, I guess, species. So energy corresponds to species or color. And then we have these hardcore interactions. Okay. And then we have also bare density of states. Bare density of states, or there's some word in thermodynamics or chemical physics. Fugacity or activity is a coefficient, is essentially bare density of states. Okay. So there's a bare density of states, which will assume to be constant, G0. Okay. But before I turn on this hardcore repulsion, okay, once I turn it on, so there'll be some exclusions, and the density of particles, of these fictitious particles, will be reduced. This reduction is the Coulomb gap, Coulomb gap effect. Okay, so now it's the same as the so what I want to do then is to do the thermodynamics, so calculate the partition function of this gas, and derive density from that partition function. This is delta again stability criterion. So I'm just what I'm doing. I'm writing stability criterion as a hardcore potential. That's all. So how do we get density of states? Sorry, how to get density? Oh, yeah, density and density of states from the thermodynamic relation. So I get basically some pressure, some temperature, effectively, in my fictitious system, and the density according to thermodynamic is a derivative of this coefficient gamma, which is pressure over temperature, with respect to log of fugacity. So I mean, just to demonstrate that does work for ideal gas. For ideal gas, this equation of state is simple. So pressure over temperature is simple. It's just given is equal to concentration. If you have many particles of different kinds, it's the sum of concentration of particles. Okay, and so it's easy to check that if you take this derivative, then of course in ideal gas for this equation of states, it's density of states and fugacity are not changed; they equal, which means the density back in the original problem, density of states equal to bare density. Okay, but if you have now a gas with some kind of interactions with some repulsion, right? Thermodynamics the equation of state will be modified. So this pressure will be different. So to calculate the pressure, just as usual, take a log of partition function. Okay, so reading various things on thermodynamics. Actually, I was teaching the class. You learn things. So, for example, I finally learned the virial theorem for the classical gas. So it's a statement about pressure or pressure divided by temperature, and it looks like this. So it's exact theorem. It says that okay. So this equation of state, so B over T, has a correction. So the first part is ideal gas equal to density. Okay, and then if in general there is a correction, which is can be written like this. So if it's hardcore, it looks like this. It's the density squared times the hardcore radius, okay, and times another quantity, G. Okay, what is G? Is a density correlation function. So it's a probability to find another particle at a prescribed distance. So in general, it's a function of distance. So find another particle at the prescribed distance r. Okay. So in virial, for hardcore, you need to put the distance equal to the hardcore radius. Okay. So
somewhere excluded volume is somewhere hardcore means that you effectively your system has.
Yeah. So I will talk about excluded volume and the hardcore radius. So if it's but I guess I can also do. So if you have one-dimensional gas, okay, I guess we can talk about excluded length, right?
Yeah.
Length. So excluded length will be r on both sides. So if you want to have an image in your head, imagine that for simplicity, all the particles are the same. Instead of multicolor, just suppose it's all the same kind. Okay, so it will be then kind of like disks or something.
Yeah.
Okay, moving on the line. The radius of each disk is r/2. R/2. So that minimal distance the two disks can come together is r. Okay, but you cannot come closer to r on both sides. So one particle will exclude 2r from the entire system. Okay, and that's going to be important. Okay, but this is R. This is the minimal distance in this formula. Okay, so I introduce this G. What do we know about G? This is a hard thing to calculate in interacting or strong interacting gas. Okay, so if there's no any kind of interactions beyond hardcore, I guess it's mean field. If there are very weak correlations. So imagine you do have this hardcore interactions, okay, but the gas is really dilute. Okay, so sometimes just particles come together, experience a collision, but that happens really rarely. Okay, so triple collision, whatever, it's very rare. So in this case, it's a very dilute gas, weakly correlated gas. This G function looks like this. Of course, you cannot come closer to a distance closer than R, so here G is 0 here. But otherwise, it's free. So it's equal to 1, probability equal to 1 for any distances larger. This is a case of a weak correlation. Okay. What happens if you have strong correlation? So, I mean, the example of like ultimate correlation is a crystal. So the particles stay at prescribed distances. So in a crystal, this G function has like kind of like equidistant peaks. Okay, so here, of course, it's not a crystal; it's still a gas or liquid. But like if you look at what it's known about this relation functions, especially in 1D, where many things can be solved exactly. So the hardcore gas of rods is so-called Tong's gas. So there's the exact solution to that you can find in the textbook. It looks like this. So here, density actually, density correlation function is enhanced beyond 1. Okay, and this is kind of first peak. Then there is another peak at distance 2R and 3R. So it's kind of like a crystal, but kind of more like loose. But there's kind of this peaks. So basically, for weak correlations in the system of hardcore gas, G is equal to 1. If it's strong correlations is usually larger than 1. If it's like really closely packed, it shoots up really high. Okay. Anyway, so if we assume the simplest thing in field field, weak correlations, is just like the graph here on the bottom, put it to 1, okay? Then we have our equation of state, okay? Then we take a derivative to get and solve this differential equation, and this is a solution, and this is a solution, okay? So this is solution for my fictitious gas. For density of states, the corresponding equation looks like this. Okay, so G, density of states at NG is equal to bare times this exponential factor. Okay, and this exponential factor is given by this 2RG integrated over. Okay, so what's the meaning of this? This equation which I wrote. It's actually the original version of Efros' self-consistent equation. And his derivation was kind of like this. Okay, so we have a stability criterion to satisfy. So we need to clear out the states around a given particle within the area, or I guess in 1D, within the length of total distance 2R. So 1R on one side, 1R on the other side. Okay, so we need to clear out. So if you have random sites with Poissonian distribution, the probability to have a void is exponential. So we need to write exponential of statistical weight, which would be there without constraints. So that's why it's going to be integral over energy, density of states, and the total length, R on each side, to R total. Okay, so this is the original equation, and you can solve it. This is sufficiently simple. So this R, I remind you, it's 1 over R epsilon minus epsilon prime. So you can take some derivatives, and you can solve it. This is the exact solution of that equation obtained by Reich and Efros. and the coefficient is 2. So it seems like, so what's the big deal? Because I just told you that numerical simulations is exactly consistent with that. So the problem was that that was the original version. But later, in all the subsequent papers, it was revised. It was revised, and the coefficient 1/2 was inserted. The argument was given that this 1/2 avoids double counting. So this is kind of subtle. So in fact, there's an interesting footnote in that paper, in that famous paper. So this says that actually, if we do, we say, if we do the perturbation theory, if you do a perturbation, we don't show the calculation, but it says if you do the perturbation theory, perturbation says there is no need to insert any 1/2. Okay. However, if you do put 1/2, it's consistent with more agrees more with simulations. So I don't know, because as I said, simulations actually show that you don't need it. So this is argument from in the body of the paper, which says that why is it double counting? As I said, basically it says that it's the stability criterion is between pairs of sides, between pairs of sides. So if you have only look at the particles to the right of you, that basically has all the inequalities in this. So you don't need to. But I cannot make this connection. In fact, this is I guess I got it from a library and I Xeroxed this, so I had it in my office. And the previous person who read this left a question mark there because it's not me who put it; it's a previous reader of that paper with the question mark. Okay, so going back to my fictitious gas. Inserting 1/2 in that language would correspond to kind of essentially assuming that okay, so I said if you can have mean field when it's 1, and if you go to strongly correlated, you expect it to be larger than 1. But this construction goes in the opposite direction. So so they reduced it. So it says like actually correlation function is not 1 but 1/2. Oh, okay, I need to speed up, but I'm pretty much done. Okay, now excluded volume. So apparently, actually, this question of excluded volume has some historical precedence, and it bothered a lot van der Waals. So van der Waals also has an equation of state. There's equation of state, and the parameter B there. Parameter B is relates usually to excluded volume. Okay, and it's written in textbooks that this excluded volume is equal to 4 times molecular volume. Okay, but if you look at a collision of 2 particles, and the total volume excluded by 1 particle is a double volume of a sphere, which means 8.
Double radius.
Right.
Double radius.
So here R is the diameter. So van der Waals, he wrote the correct equation. This is correct. So if you have to put this 1/2 to have a correct virial expansion. But he was also bothered by the fact that he have to put 1/2 in that. And there's some people who said that you can understand it if you this enigma. Anyway, so for me, I mean, looking back to van der Waals, if you want to have a correlation function less than 1, you would need to have some kind of like attraction. Because if repulsion only, hardcore repulsion, gives you 1 or above 1. So some kind of mysterious attraction maybe, or I don't know. But I need to hurry up and finish my talk. So okay, so I said that we have this mean field equation without any artificial corrections. It gives you correct results, which agrees with simulation. However, it's still puzzling because, I mean, the final result against the states goes all the way down to 0. So it's a big effect. It starts from bare states, but it goes, how come we can use mean field? So it seems like a related system, right? Excluded area is large. Well, it's large, but it only grows logarithmically. So the argument is that indeed correlations ultimately going to be strong in some sense, but if it's logarithmic growth, it can be taken care of by renormalization group calculation, which is justified by some logarithms. So you can write this partition function, and basically formulate some RG technique to see how this partition function evolves as you decrease the cutoff, so approaching the Fermi levels. And so this RG goes to indeed to weak coupling. So maybe I should skip. How much time I have? 0?
No, it's 4 minutes. It's 3 minutes.
Okay, 3 minutes. Okay, so with some RG equations you will derive for these fugacities, and they have the original form of Efros, so without any 1/2. So then it seems like this, I would think, more controlled calculation says that everything's fine. So the new theory, well, not new, but I guess Voigt and John had a similar equation, 1993, with coefficient 2, is the original Efros equation. It agrees perfectly with simulations in 1D. So the only thing is that actually been other previous renormalization group approaches to Coulomb gap. I know of 2 examples. Maybe somebody knows more. I know a theory by Mogilyansky and Reich, who tried to do Coulomb gap, who looked at the Coulomb gap at final temperature, and they had some procedure. Instead of changing cutoff in energy, we're changing cutoff in space. Okay, so they got C equals to 1. The reason they got C equals to 1, like, because they also by hand reduced the coefficient factor of 2 and referred to Baranovsky 1980, because it's all explained there. Okay, so I actually asked Misha, right, why did he do it? He said because he believed in that paper that everything's taken care. Yeah, so because Boris is right. Okay, there's another paper, RG paper by Khmelnytsky, that's his student, which gets also agrees with with Boris again, with modified equation. I don't understand this paper. We calculated using some non-traditional diagrammatic technique, and there are no details. It just draw some diagrams, and these diagrams I don't understand what they mean. So they're not standard diagrams, and so I don't know why, but this is what I have, and it's I guess reconciles so far the discrepancy. So where do we go from there? Well, I don't know. Higher dimensions is harder. So how to do this? I don't know. Maybe epsilon expansion will help a little bit to go higher dimensions. And in terms of experiments, so I promised to show one data. So there was data, tunneling data by Bob Dines into tunneling into aluminum wires, which I guess it's not enough data to like resolve the coefficient of its logarithmic law. We show some evidence of logarithmic 1D gap. So otherwise, most experiments were on 2D and 3D. So tunneling is one way. The Coulomb gap was also previously observed in photo emission data. So maybe it's also be interesting to look in other experimental probes, because tunneling is very tricky, time-consuming, and so on. So maybe photo emission is in a large area. So it was done for some organics and so on many years ago. But otherwise, thank you for your attention.
Good. Questions?
Your question about van der Waals. So what happened with van der Waals?
So
I mean, it's still not clear.
no, I think it's clear. So I mean,
Something.
this is a correct This result is correct. This is correct. This is a correct coefficient. It satisfies the virial equation and so on. Okay. The only problem, if there is a problem or enigma,
Oh, you try to interpret it. You
is when you try to interpret it in terms of excluded volume.
wanna get A.
Okay. Essentially, he got it right. He put it 1/2 because it's binary collisions. Okay. But my equation, this equation, my equation includes that. I don't put 2r here. Here I put 1r as you're supposed to do, is what Van der Waals did and other people did. But when you solve them for density of states from this correct equation, you get this. You don't get 1/2 way. So in other words, I mean, I agree that there is a. I agree with this. This is all true, but I don't know. I don't know how to connect second sentence to the first sentence.
Questions? So you get RG with more temperature.
There was no temperature, but there was a cutoff
So when it's just
because it's hardcore interaction. Temperature doesn't really play any role, so it's just overall factor which eventually disappears.
it just in a couple of temperatures. Maybe not.
It doesn't matter. Just there's no temperature. It's inside of this. Okay,
Right. So,
but it's immediately there is a pressure, but it's immediately divided by temperature.
right.
So the only thing which appears is just this gamma, and so whatever the T is, if you rescale it, it doesn't.
All right. Those are all the questions. That's it. First, and we're talking about something about nanocrystals. Okay. Just
Does it work?
yeah.
Good afternoon, ladies and gentlemen. Before we get started, I would like to thank the organizer for inviting me for this important for me event, Boris' 80th birthday. I initially thought that I was invited because of my last name, because Boris has so much collaboration with persons with the same name, and that is why I initially want to talk about some result on novel result on application of Boris and Alyosha's idea in new structure nanoplatelets. But yesterday when I came, Boris told me, Sasha, are you going to talk about Nobel Prize? I said, maybe this is more interesting. So that is why I decided to switch topic and talk about semiconductor nanocrystal from discovery to modern development. As you might know, the 2023 Nobel Prize in Chemistry was given to Monge Bawendi, Louis Bruce, and Alexei for the work on discovery and synthesis of quantum dots. So that is why I will dive in history of nanocrystal quantum dot discovery, a still surprising and interesting property of nanostructure. Similar to opening the Russian doll, delving in the history of nanocrystal reveal many interesting and intriguing properties. And in my talk, I will present only my theoretical perspective on this still fascinating narrative. My research in this area is supported by U.S. Office of Naval Research. For people who don't know what is nanocrystal, here I showed you an image of cat selenide nanocrystal. For chemists, it's just big molecule which atom organized in bulk crystal structure shown here. And current technology allows to change the size of this nanocrystal from couple to 100 nanometers in controlled manner. For physicists, especially theoretical physicists like me, nanocrystal essential three-dimensional potential box, which confine free motion of electrons and hole leading to size-dependent discrete level structure, a discrete spectrum of optical excitation. Recent advances in fabrication, physical understanding, in application on a crystal, driven by intense interest to the unusual potential use of electronic optical property. As a result, broad class of semiconductor was prepared in nanocrystal form, including recently perovskite, size and shell control tunability of the electronic and optical property. And here as example, I show you size tunable absorption and emission of cat selenide nanocrystal. Color of the line reflects the real color of emission line, combined with ability to manipulate this freestanding nanostructure with nanometer precision, open exciting opportunity for develop novel functional material for a broad range of applications. The structure allows bottom-up chemical approach to assembly. Nanocrystal can position and assemble two-dimensional, three-dimensional supercrystal, consumer design nanocrystal molecule, and functional nanocrystal biomolecule conjugate. As a result, multiple application of the fundamental property of this nanostructure is closer than ever. As this research in nanocrystal already was transformed production of commercial devices. So 2011, NanoScience announced product called quantum dot enhanced film. It's a film of nanocrystal, which excited by gallium nitride laser and generate red and green light. So you have three color gamma. And at the same time, Samsung announced product which called display with high definition, low power consumption. In commercial liquid crystal display, you can compare this to picture. And today you can go to Best Buy, buy the quantum.tv, still rather expensive. And the production of this TV is $3 billion business in Samsung Corporation. There are no doubts that nanocrystals are most heavily studied among all nanoscale semiconductor. The size depends on nanocrystal optical property, was discovered independently in semiconductor doped glasses by Alexei at that time Vavilov State Optical Institute, and Louis Bruce, in that time a Ballet in aqueous solution. Unfortunately, I don't have picture of this pioneer in the moment of discovery, but I can show that they look much younger than they look today. Here is a slab of glass which Yakimov prepared in 1984. This artifact was served as the first demonstration of Econ's special quantum confinement in nanocrystal. The glass contains homogeneous concentration of gas selenide. Our gradient of temperature was applied during nanocrystal growth. As a result, large nanocrystal grow at this edge of sample, small or none of this edge sample, leading to gradient change of the slab from red to transparent. There's a lot of similarities in this discovery. In both cases, nanocrystal growth is the result of phase separation of separated solution. Nanocrystal is essentially a nucleus of new phase. like it is like droplet of water in supersaturated water. Size of nanocrystal controlled by diffusion and atom or ion to the growing nuclei. The final size controlled by duration of growth and at fixed interruption, so-called arrested precipitation of sizes. And research in both cases was driven by pure curiosity. Neither Kimov or Bruce wrote proposal. They want to know what determines color of glass, means glass, clouds nanocrystal solution, or in the glasses, and administration of both Vavilov Institute and Bell Lab supported this research. Yes.
What's the difference from glassing in medieval cathedrals?
It's the same.
It's the same.
It is a long story, but this technology was brought from Germany to Russia as part of reparations. Foreign glasses. So analogy with superlattice and explanation why color nanocrystal correlate with the science come from existing of the two-dimensional superlattice. Different was that Ekimov measured size of nanocrystal using small angle X-ray scattering. Bruce used TM. The difference was interesting, however. Nanocrystal was prepared in Soviet Union before first superlattices, which was grown in Alferov lab only in 1984. So if Bruce has opportunity to discuss his result with his theoretical colleague Bell Lab, Ekimov didn't have this opportunity. So he found his neighbor, me, to discuss theoretical aspect of nanocrystal. We live in two apartment houses standing next to each other. And we spent each evening sitting on his, on my identical 7 square meter kitchen, discussing optical properties of nanocrystal, drinking tea, and sometimes something more strong. So today it's almost impossible to imagine initial skepticism of solid state community of Soviet Union that nanometer size particle, which contain only 300, 600 atoms, could have regular optical property which controlled by just one parameter, nanocrystal size. In order to publish our paper, we call this nanoparticle microcrystal, because otherwise it wouldn't be published in Soviet journal. Because this nano didn't exist in Soviet Union before Alferov growth first quantum world. So, but critically, the technology developed by Ekimov allowed to grow nanocrystal with well-controlled size, gradually change size from 2 nanometer to practically microscopic size. And this size dependence, he established size dependence of 4 compounds, and they're pretty well described by effective mass theory. And this slowly changed the attitude to this research. And here, example, I show you absorption spectra of copper chloride nanocrystal, low temperature absorption spectra, measured in nanocrystal with radius 2 nanometer, 2.9 nanometer, and 31 nanometers is blue curve. This large nanocrystal spectra absorption practically identical to absorption spectra of bulk copper chloride, which have 2 subband and 2 exciton connected with this 2 subband. Here I show the size dependence of this position of these 2 peaks, plot as a reverse square of nanocrystal radius. This size dependent very well standard expression of particle in a box model with only one fitting parameter, effective mass of action. Here I show you low temperature absorption spectra of cut sulfide, again 1.2, 1.5, 2.3 nanometer, and again giant nanocrystal 33 nanometer, shown by red line. This absorption spectra of large nanocrystal identical to absorption spectra of cut sulfide. You see fine structure connected 3 valence subband of cut sulfide. The decrease of nanocrystal size shifts the absorption band age, it leads to some oscillation in the spectrum. This shift, 1 electron volt shift, connected with optical transition between quantum confined level in this material. In spherical approximation, each electron is state characterized by angular momentum 0, 1, 2, and again, energy spectrum described by standard expression, which you can find in any handbook on quantum mechanics. It inversely proportional square of nanocrystal radius, inversely proportional to effective mass, and phi a root of some spherical basis function. And this cartoon I show schematically position of the electron hole quantum confined level calculated parabolic approximation, where we borrow atomic notation SPD for state with angular momentum 0, 1, 2.
Spherical.
It's
Okay, spherical.
spherical approximation. The linear absorption spectra described by this also simple explanation. Selection rule in parabolic band approximation allow transition only be within level the same quantum number from first to first, second to second, etc. And linear absorption spectra, it is bulk energy gap, energy of confinement of electron, energy of confinement of hole with the same quantum number minus energy electron hole Coulomb correlation, which can be calculated perturbatively. So here I plot again position of the shift of absorption band tension and I plotted the reverse square of nanocrystal radius. It's not linear like in copper chloride due to non-parabolicity of electron effective mass. Electron become heavier, there's bending. This spectrum doesn't show any structure connected with hole transition because dispersion of this sample was 15%. And this dispersion completely washed out the structure of hole level. Hole level will reveal only 9 layers later when Kim was able to reduce dispersion of nanocrystal sizes to 5%. And here you see absorption spectra and spectral second derivative for cat-selenide nanocrystal with radius 3.8, 2.6, and 2.1 nanometer. This absorption rate cannot be described using parabolic band approximation equality because valence band consists of this subband and selection rule are different. And theory was developed in this paper. And here I show the site-dependent position of lowest electron hole level calculated in this paper. You see quite complicated structure of hole level. There's crossing and anti-crossing. And there's no selection rule connected with main quantum number. Transition to 1s allow from all mixed SD level of hole, P level, all mixed PF level of hole. And using this optically allowed transition, we calculate oscillated transition strength. And we shown here by vertical segment and pretty good describe a measurement of Ekimov. I believe the 40+ years of nanocrystal instigation can be separated in 2 well-defined periods, BTP and ATP. What means before Z paper and after Z paper. So in 1990, Monja Bavendi, Louis Bruce postdoc, moved from Bell Lab to MIT. He found 2 extremely gifted students, you probably know them name, Chris Murray and David Norris. David Norris was professor here, by the way. And they published paper which provides first reliable growth of nanocrystal with small distortion of sizes for broad region of sizes. And here I show 3 critical figures from this paper. First show narrowing of nanocrystal size dispersion using size selective precipitation. Second show remarkable control of nanocrystal sizes from 1.5 nanometer, 1.2 nanometer, again, color reflect emission line. And that this technology allowed to grow nanocrystal, not only Castle-9, Castle-5, Castle-9, all 6 components. Months ago, I saw this paper was cited 12,000 times. And that is why Monja Bavendi got his Nobel Prize. So the technology developed by Chris Murray has big advantages versus technology developed by Ekimov. Ekimov could control nanocrystal sizes, but extraction of nanocrystal glass would be a problem And this technology allowed to have powder nanocrystal, use them for build up some structure, some devices. So thousands of people work using this technology for various devices. And although Chris' paper provided technology paves the way to many new potential applications, the further development were critical for this development. First of all, a successful growth of core shell structure reported by Highness, Philip Jones, CMS. They increased photoluminescence efficiency of the structure to 50%. And here you show the figure from original paper. Intensity of luminescence increases by factor 6. Growth of three-dimensional periodic array of nanocrystal. This paper, you see TM image created from three-dimensional array, grow from 5 nanometer diameter Cas9 nanocrystal. This paper has great potential because instead of limited number of kind of atoms which nature gave us, you can do something like unlimited number of different nanocrystals with different shape, with different chemical composition. Unfortunately, the promise never was realized yet. Another progress, it's control of colloidal nanocrystal shape. Pink in the polarizated growth demonstrated that some precursors allow to grow strongly elongated nanocrystal. It is so-called nanorods. Another important development was demonstration of that nanocrystal can be used fluorescent biological label. And here two-color labeling of mouse fibroblast with green and red quantum dots. However, this labeling was done in vitro. Another important technological development, doping of nanocrystal with impurity. David Norris successful dope zinc selenide nanocrystal with manganese, creating high quality of nanocrystal. And you see photoluminescence from manganese in this nanocrystal. The fine structure of EPR of manganese, which correlate with position of manganese relatives of zinc selenide. A final giant circular dichroism connects with giant magnetic field of manganese silicon nanocrystal. He also not only demonstrated, he shows that initial idea why it's so difficult to dope nanocrystal. Explanation of self-purification is wrong. Discovery of new safe agent reported by Penk again. It was very important because early the agent used by Chris Murray was toxic, paraphobic, expensive, unstable at room temperature, a result of several accidents, including Bruce, who was injured during work with this precursor. More impressive result, control of colloidal nanocrystal shape. The Sandrine and Benoit Dubertet demonstrated that you can grow so-called nanoplatelet, the freestanding layer of semiconductor, which contradicts, from my point of view, common sense, what we can grow in solution, because we can understand why nanowire grow, why nanorod grow, but it is free layer of nanocrystal, and the explanation currently why nanocrystal grow. Here you see the TMH of such 5 monolayer 6 Cas9 nanoplatelet with lateral size 20-30 nanometer, and here this nanoplate has optical property of two-dimensional quantum well, how you see here. Here's the absorption factor, photoluminescence measured 2, 3, 4, and 5 monolayer nanoplate. Another fascinating development, reversible cation exchange. It was shown that you can completely remake nanocrystal without changing its annual lattice. It was demonstrated in polarizated group. And here you see Cas9, which you transfer to aluminum silver selenide, and reversible exchange back to Cas9. And these 3 panels confirms this remarkable transformation. X-ray diffraction, fluorescence absorption. finally, maybe not finally, but now, but introduction of inorganic ligand that increase significantly electrical coupling between nanocrystal, which allow to have photoconductivity in the structure, transmittance. So widely tunable absorption spectra will clearly transfer to widely tunable emission spectra. This and here shows size tunable emission spectra of indiarsenide, indiphosphide, and calcilinide in combination with great chemical flexibility. One can grow alloy of nanocrystal, one can grow array of nanocrystal, one can grow solid of nanocrystal. Combined with great optical stability, one can put billion of photons through nanocrystal, property doesn't change. Determines the major nanocrystal applications. So photoluminescence of quantum yield of nanocrystal grown today routinely can be 70–80%. Turn out that the fact that luminescence is not 100% is not sufficient for some application, and turn out that this under not complete photoluminescence efficiency is intrinsic property of nanocrystal. So imagine your irritation and frustration if bulb of reading lamp start to blink. Exactly the same feeling experienced scientists at Bell Lab when study photoluminescence of single nanocrystal and discover that each nanocrystal exhibit intermittency of photoluminescence intensity. And here you see the figure from original paper. The intensity of time dependence of intensity of luminescence that exhibits sequence of on and off period. For particle covered by zinc sulfide shell, duration of on period is much longer than duration of on period in bare particle, which dark almost all time. Since the paper was published, the blinking behavior was discovered in all nanostructure, at all temperature, porous silicon, nanowire, whatever.
Luminescence, they shine some white light on it, and
They shine steady-state light. It can be any frequency.
but the output is
Output is good. You need to integrate. It's a single quantum dot. You need to have some bin when you collect it. This is why I think bin is written here. So when it was first discovered, it come complete surprise. Today, the consensus, the blinking connected with fact, the under-illumination nanocrystal can be ionized and so charged and then neutralized. Indeed, if you have neutral nanocrystal, photoexcitation of electron hole pair can generally lead to only to luminescence. Electron hole pair relax and emit light. If you excite charged nanocrystal, the trigger process, which is known as non-radiative phase recombination. It's a process with which annihilation energy of this pair go to some extra carrier. As this process standard nanocrystal much faster than radiative recombination, 1000 picosecond, and so luminescence completely quench in charged nanocrystal. So if you look on this curve, it is clear that at some point nanocrystal got charged. Then after some time, ejected from nanocrystal come back and restore neutrality and again see luminescence. How this occurs still remain history, and many groups trying to answer this question. Probably there are multiple answers to this question. Theoretically, three mechanisms of nanocrystal ionization was suggested. First, direct quantum mechanical tunneling of electron hole to the surface trap, or thermal injection of electron from nanocrystal with small upset, or array ionization of nanocrystal, where simultaneously create two electron hole pair. In this case, annihilation of one pair can go to the ejection of particle out of nanocrystal. The efficiency of this process depends on the size of nanocrystal, temperature, band offset, matrix, etc., etc. Clear neutralization occurs through quantum mechanical tunneling or through thermal injection. So trying to understand mechanism of nanocrystal neutralization, people study statistics of the on and off behavior and discover the duration of on behavior or off behavior described by power law when u is between 1.4 and 1.8. And this imply easily absence of average photoluminescent dark time period or bright time period. And has some very unpleasant practical consequences, because if nanocrystal is in dark state, you cannot predict if and when it come back and become bright. There are several efforts to suppress blinking. One of the most successful grow nanocrystal with 6 shell, first reported in these 2 papers. Indeed, no matter how ionization occur, 6 shell would prevent electron and hole escape to the surface. And it was clearly confirmed by the single quantum dot measurement by Mahler paper, which shows this longest offset of off period. But most of nanocrystals still continue to blink, and this riser mechanism can be suppressed Auger process in nanocrystal, which is main responsible for this blinking behavior. To answer this question, let's consider first, let's explain first why Auger process is so efficient in nanocrystal. It is well known that bulk wide gap semiconductor like cat selenide or cat sulfide Auger process generally suppressed. Let me explain how does it work. Let's consider Auger process of 2 electrons with hole in bulk material. After annihilation of this electron hole pair, its energy go to second electron. And this process should satisfy energy conservation, which is bulk energy gap, kinetic energy of electron, kinetic energy of hole, equal to kinetic energy of electron in final state, and in bulk momentum conservation. It clears that after Auger process, this electron has very large kinetic energy. The large kinetic energy associated with large momentum, and the large momentum associated with large kinetic energy of the initial part. Solution of these 2 equations shows that the indeed kinematic energy threshold. All the particles should have enough kinetic energy in order to Auger process happening. And this energy, kinematic energy, proportional to the energy gap. So it's clear that Auger recombination in wide gap semiconductor described by some Arrhenius law, when its exponent we have ratio of energy gap to temperature, and that is why Auger process suppresses wide gap semiconductor. However, in nanostructure, the lifting, you have lifting momentum conservation and remove energy, kinematic energy threshold. So Auger process always happen, could happen. Question is how they're efficient. In order to calculate Auger process, we need to use Fermi-Golden rule, where the major problem of this Auger process calculation estimation of this matrix element taken between initial multi-particle state and final state where electron and hole is highly excited state with large momentum. At the first glance, the magnitude of this matrix element should be on the order of average Coulomb interaction energy. However, this is the wrong answer, because electron hole in final state oscillate rapidly. Integration of smooth function is rapid oscillation function, give you 0 in first approximation. In order to find this matrix, you need to find Fourier component with momentum, with much momentum to the electron in final state. And this momentum produced in some point of nanocrystal. For example, in the place where particle kinetic energy or the uncertainty has maximum. For example, if you consider Auger recombination of exciton bound to neutral donor, so the 2 electrons in 1 hole, Auger process can happen. Auger process happens right at the center of Coulomb impurity, because at this place, potential going to infinity, kinetic energy to plus infinity, so it's a place where electron pick up energy. In case of nanocrystal, Auger process happen right in nanocrystal surface due to large uncertainty of momentum. It's why Auger process so efficient, small size nanocrystal, the large surface to volume ratio. So this quality of consideration already tell us what you need to do in order to suppress other processes. You don't want to have these abrupt interfaces which promote electron to pick up momentum. You need to have smooth confinement potential. And this can be confirmed by analyzing Fermi component of the localized state in the quantum dots. And this qualitative consideration we confirm by direct quantum mechanical calculation of rate Auger process in abrupt quantum well and soft quantum well. And here you can compare the rate of Auger processes in soft quantum well, which is several orders of magnitude lower rate than in abrupt interfaces. And indeed, recently, Viktor Klimov grow quantum well with continuous great shell. In these quantum dots, they didn't see any blinking behavior. And for comparison, he also showed in his paper standard giant sulfide selenide nanocrystal. We show some blinking behavior, also wandering the exciton line. And this quantum dot was recently used in order to create electrically pumped quantum dot laser. It's the first report on electrically pumped laser, which was reaching this quantum dots.
Why is it giant?
A giant because core is small and you grow very thick shell in order to suppress escaping of electron from the. But there you see the line still blinking. So how much time?
About 5 minutes.
By 5
Very
minutes. All right.
7 minutes to the very end, and 5 minutes if you leave a couple.
All right. So I would say that 3 years before the paper, Monja Bavendi in the Bell Lab wrote first high quality crystal, which we show quite pronounced peak in absorption, quite narrow luminescent line, and high any quality sample. In this sample allowed to measure new physical phenomena. The resonant excitation of the luminescent line show fluorescent line narrowing with exhibited zero line and optical phonon assisted line, all shifted with respect to photo excitation by 18 MeV. And this luminescence has very long decay time, 1-3 microseconds. Later, this fine structure, the long decay time, was explained in the dark-bright exciton model. In this model, electron hole exchange interaction splits the bent edge exciton into state with very different oscillated transition strengths, bright and dark exciton state. So we optically excite one of the upper bright exciton state, then exciton relax to the ground dark exciton state, which have long decay time. This explains stock shift and long luminescence. Here, I don't want to discuss it, more exact calculation of this exciton fine structure. This exciton, they have 8 band exciton and cat-selenide nanocrystal, and the electron hole exchange and crystal field split this exciton state in the 5 exciton sublevel. Lowest exciton level is dark exciton, which has projection ±2 on the axis of hexagonal axis. It is dark because you need 2 units of angular momentum in order to relax electron hole pair, because photon can carry only momentum 1 electric dipole approximation. So in the bulk, when the splitting is small, you equally populate bright and dark exciton level, and you see quite transluminescent. In cat-selenide, the splitting is 20 MeV, even at room temperature. The splitting is too large to populate upper state, and that is why decay time in cat-selenide 20 nanoseconds. This fine structure was studied in all possible nanostructure, and there was common belief the ground exciton state should be always dark optically forbidden exciton. However, 6 years ago, Maxim Kovalenko grew a new class of stadium led halide perovskite nanocrystal, which emission cover entire region of optical spectra. They show this nanocrystal has cubic shape and they show remarkably bright photoluminescence at room temperature, which have 50-90 quantum yield. This quantum yield was straight down surprisingly fast emission lifetime, which in room temperature is 20 times shorter than capsulinite. At the helium temperature is 250 picoseconds, 1,000 times shorter than was measured in capsulinite nanocrystals. So it looks like shortening of radiative decay time is decrease of temperature is not consistent with dark exciton model. Because if the ground state is dark, at low temperature you have long decay time, rising temperature, you populate bright exciton state, you shorten decay time. And this right equation is a ground exciton in the perovskite is bright. So we calculated fine structure of this exciton, but right now I want to mention only that I don't have enough time. There's 4 exciton states in perovskite connected with top of the valence band and bottom of conduction band. And if you make electron-hole exchange, there's a ground state exciton as optically forbidden dark exciton state. And upper bright exciton consists of 3 lines due to orthorhombic perturbation. This bright state, all of them 3 linear polarized. So what you would expect from such structure of level, you would expect single emission coming from dark exciton state, slightly affected by upper dark exciton state, bright exciton state, is not what experimental data show. Experimental shows that in single quantum dot measurement, you see 1, 2, 3 spectral feature in emission. All of these lines are linear polarized. And this raises a question how this upper exciton state can emit light. So in our nature paper, we suggested that if a nanocrystal has Raspberry atom and conduction and valence band, the effective exchange interaction between conduction and valence band allow us to create electron-hole exchange, additional created with Raspberry. And if Raspberry coefficient conduction band and valence band are the same sign, the upper exciton become dark and 3 lower exciton become bright. And you can see this emission from this exciton. Where this Raspberry atom come from? It was recently discovered that low symmetry crystal phase exists in selenium lead bromide material. And more recently, it was explained by low power stereochemically adjusting ferroelectric distortion in this low temperature, which allow to have low temperature phase. There's another explanation of this phenomenon, connects formation of bottleneck. Yes, just a second. Just one figure, yes. Finally, I want to show that this bright exciton, which upper 3 bar exciton, have very short decay time due to giant oscillator transition strengths introduced by Professor Raspberry in 1961. Because in this nanocrystal, the size of exciton is much smaller than size of quantum dots. And this ratio of volume quantum dot to cube of Bohr radius brings the radiative decay from nanosecond to 100 picosecond, which was measured in this perovskite material. So I don't have time to discuss future in this case. I want to acknowledge people who contribute to my research. First of all, Alyosha Yakimov, who brought me to this research. All this experimentally this whom I collaborate is important to overestimate the role of my discussion with them. Theoretician from Yoff Institute, from NRL, Iran Ribani, Peter Cell, and 4 of my former postdoc who conduct most of this calculation. And this is the end. I would be happy to have any question if you have time for this.
Thanks, it's great. Just,
What if you put this nanodot on a metallic surface? Is there plasmonic enhancement? That's one thing. And then blinking, can it help get rid of the blinking? Putting nanodots on the metallic.
So plasmonic. It is known that plasmonic effect, it was done in, I believe, Bavendi group. So he put nanocrystal surface of large plasmonic particle and blinking was suppressed. But it was not suppressed because Auger process was suppressed. It was suppressed because dephasing into the metal particle occur much faster than Auger.
Meaning the electron would return. Okay.
Yeah, I have a question. So you mentioned that you or someone made a laser with those quantum dots.
Yes.
Can this laser be tuned by changing the size of those quantum dots? Meaning
Sure.
the
They demonstrated, yes.
okay.
So they clearly they know how to make soft confinement profile using multi-shell structure. The multi-shell structure can be adjusted.
So there may be any wavelength achieved for those.
I don't know. I saw only one paper from Plymouth.
so we're going to putting in is, what is, 10 minutes before.
Можно с тобой вопрос? Значит, это вообще какая-то очень старая проблема, не разрешена.
Oh, how are you? Right? I understand.
Yes,
It's hard to
кстати,
get away when you're here.
но вы можете писать, но люминесценция будет подавлена. Потому что вместо выбора дается там электрон или дырка. Вы выбираете электрон дырочный класс. Но она не рекомбинирует, она идет уже, потому что это рекомбинирует, а передает энергию. Один escape, второй там. Ну, вероятность того, что два escape, очень низкая. Значит, один. Да, и тогда у вас значит, произойдет ажиотажный процесс, который называется 10. Он будет быстрее.
You don't have this usually once here, right? Like undergrad.
We don't know what's going on. We're trying to in low range. So it's true that all the students.
That you might appreciate.
No, but one of the stories Borya asked question where the technology came. This technology came from in 1850s, from Corning glasses. Because like part of preparation, all the equipment was brought to Russia in Vladimir. The critical step, which he came up with, he is quite good physicist. He has another advantage, not only he, and you know, color, like you said, was chemical composition. Selenite, zinc selenite. You do this chemical composition, just selenite.
Yeah.
And this you make a deal. It turned out that
That's how you get it. But yeah, well, it's between like the different areas.
Yeah.
Really dramatic.
ну что выпиваем?
But I guess we did it.
Один есть, надо третий. Компьютер.
Something like peace.
And they were really good. Like the first semester I had 20.
Right.
And then the second semester.
So you don't have that, you don't have that? Well, then I guess people just skip it.
We do have some. I mean, actually, there's only research university in the States, and we have. So you had some disaster.
Oh, yeah, our roof blew up.
Yeah.
Oh, yeah. And but it was wonderful. You know, insurance came in, I guess, and it was like, we've lived in it for 6 months, so we learned both. So it's all worked out. But yeah, 'cause when I came and visited in 2010.
Oh, no, 2010, that was the other.
So I came in 2010 and 2016.
It's the German generator. It's like piece of very. And that's how the brain works. All of us. That's what
There's some that they will think about. We don't have them. They also have potential, constant. And then content. The first soul is
First of all,
Simply also not completely free.
Local sculpture.这些地方，
一个背景。
反正是我要知道我的位在哪，我就 step 上面。
Maybe.
very least it's.
Well, no, but of course, they were.
You're gonna What are you gonna do with the rest of the 30 minutes?
Evolve them first. It's maybe something else. And it's maybe the question trying to think about it. But then another question is never. It's shape to get rid of this and.
Actually, like just calling it. It's not a lot.
Yeah.
So the, which is.
现在全程是发的，对，他们就是你手机听的是，你就会空气砸进去，或者那个你屏幕上有些小花点，对，还有一个词 change，所以我觉得有可能会有一些奇怪的，对，10,000份就以前热的，我就回东北这个，他知道上面有一堆 bubble，但他不知道那些 bubble 还能，他可能是了解，这个 bubble 就第一次可以开始有时候我们在bubble 里面去发展，可以有空气的话，里面会把oxygen 比较有高自己，所以我们做实战过程就非常慢。以前的这个分辨率下，我们可以找到一个大部分的。
在这里是这个中间这个嘛，
这是一层，地点是不一样的。但是呢，
就是本身里面是 Windows，
大六零，说我们涨没有800。
啊，就这个量基本上也是800，
对，它高度比较高，没有800，没有800。
啊，这种灰的就是
是，第三个它是这个。
那然后你这些加上去叠上去这个线，
所以我要 design 一些会，这可能比较复杂。这个这个3个差异，中间的那个包括是健身房所以包括两个。所以应该跟其他的那个应该一样的。我那里很脏，为什么？我不知道，至少我们会用，比如说我们会用 AI 来查这个写人一些的，最好是他们会跟你先找谁干，一般就先比如说扫那个时候，我们会有一些。写出来。 如果分出来 density 很高，就是那个 HBM 跟 gate gate 界面附近那个 impurity 的 density 是12次方太高了。对啊，当然了，
12次方还是那个，因为我们电子的那个 density 一般 range 都是11次方到12次之间，对，一般是到。
但是我知道，但是在其他的 semiconductor 里面，这是一个 typical 系统。Silicon 的那个再放一层那个 silicon， 再放那个 aluminum oxide 做那个 dielectric， 再放 gate， 我在 aluminum oxide 跟 gate 之间，跟那个 silicon germanium 之间，它那个 density 就是12次。
那他们是不是也负的？
跟 dielectric 就是在 interface。
我意思是它对底下的穿层，这个 Q 带的影响。是啊，
但是他们也只有30纳米。
哦，那这么，那我就不知道，那可能几期啊？12次方是12次方还是有点不同？
因为它取决于那个 impurity 比 gate 到底有多远。近的话 ，gate 会把它 spin。我用的是很简单的 spin 的东西。在 gate 里面有个 image 的。离它越近的话，就需要越多的 impurity， 因为它离 gate 越近，它就被 spin 越远。离 gate 越远的话 ，fit 出来的越远越小。假设它离 gate 有1纳米，如果离它有2纳米的话，charge，
它就是在 HBM， 就在那个
变成 gate
之间的
变成 gate interface， 但是我不能完全把它放在 interface 上，因为不完全被 spin。
哦，
它取决于它离它多远，离越远的话就 spin 越弱，离 gate 越远 ，gate 就没办法好了。这时候你去看那个飞出来可能对变化都会比较小，所以完全取决于它有多近。我根本不知道有多随便是，
那可能就是 atomic 的编制，3个4个。
是用的那个是一样的。平常我往死上再少一点不会差点吧。对，这个是我要评 fix 的，
12次方确实
买上的。
我不知道差异8代理，
这东西应该它的天地那边的那个性感觉，
它这个它自己就，
我算出来就是这样。
对，后面会有
这个点，你一个一个字就画出来。
知道，这个花时间，
这个
我提到1次方要1个小时。对，就是
这画下这些。
我标的这些信息。 有直接接触是800个，非常就是然后呢这个测一下，我要4针。有建议我去来一群帮他的地方，
你是那你
对，这个比如说，所以你需要有一个上司就是加一点这个不管你的这方，像水的
如果其他地方是保持是
其他地方对，其他地方
零
不导电，
对，它那个
只要是你把那个我出水口我给堵住了，它就不会出去。
这样就能控制它的能力。
对，但只是大概的一个东西，也跟你们这儿有一些细节的东西。但我们这一般的阶段就是抛把情况，我一般的第3步上面跟正步。
就有应该是用来测的。
对，这些差。当然我是抛把，刚刚是抛把你整个细的，当然抛把也不问题，没问题。如果那个细把它按就没有话，由他来讲，我们有机会跟他讲。很贵。
Average data 是从哪里在？
我觉得是statements。这个。如果你太窄的话，那就可能你有一部分 stage。
What? Talk to me. What is this?
这个
His sample.
这个好，结果3号，应该是丢上去新的那个。
So you have the AFM supervisor.
Of bubbles.
Oh yeah, so you're trying to write around the bubbles. That's clever.
这个绿色线就是地方，还有3种这样。
It's not just that explosion. That makes sense.
这个是应该是这个方法。
测满 level transport. Transport is probably this.
对，body 局是在 body 上，对的，加上
问题。
然后
会有些强的，就是
那你们不是说新的
Нет, нет, а если я просто всегда, тогда
但是就是说他们会有
я хоть раз Я буду сопротивление. Это мое Ну хорошо, Саша сделал, да? Я его свернул с его личного работы. Последний работа. Это очень хорошо. О, люди садят туда.
Okay, let's have a progress. So, switch gears to the subject of neurons, and the first of the talks will be given by Alex Koulakov from Neurons to students.
Yes. Arm myself a bit. Well, thank you so much for being here. I realize it's not easy, and it's my pleasure to be here. My name is Alex Koulakov. I'm from this beautiful place. It's a whaling village on the north shore of Long Island. We're trying to crack the brain. So, not literally. So, I realize that not everybody is an expert in the brain, so I'm gonna just briefly describe how the brain works. Less than 5 minutes. So this is basically how it works. So a brain is composed of neurons. Neurons have cells, which are giant.
Oh, doesn't work.
Okay. Which are giant capacitors. They look like octopi. They have two types of branches. So there's something called dendrites, which are passive waveguides. They receive information from other neurons. That information travels to the cell body, soma, where it's composed, it's added up, and then at some point, neuron makes a decision to emit something that is called a spike. The spike is like a soliton, which is basically the membrane will be short-circuited very briefly for about a millisecond, which can propagate at enormous speed along something called an axon. A neuron usually makes only one axon, so there is only one decision that it makes. And then it arrives when the spike arrives at something called a synapse, which is a connection between two neurons. There is some kind of molecule will be spilled from the synapse, and it will diffuse to another neuron, and it will produce either excitation or inhibition in another neuron. And that's how information spreads through our networks, and that's basically how the brain works. So you've already heard everything. So another interesting factoid is, I borrow it from the title of the book of my friend Sebastian Sung, is that what basically the current hypothesis that what you are, your personality, your memories, your skills, is stored in the connection matrix between the neurons. and which is illustrated, which is schematically shown here by those diffusion tract axons. Those are like connections between in the white matter. So the number of connections, of course, in human cortex is enormous. We have about 10 billion neurons in cortex. Each of them makes about 10,000 synapses. There is a lot of information we can store. So I would like to make this very simple back of the envelope estimation. What is exactly the amount of information that we can store? And so I learned this formula. We have like 10 billion neurons. We have 10 to the 4th synapses per neuron. I learned this formula that the amount of information is just the entropy is just a log of number of combinations. I can find the total number of matrices with those parameters by binomial formula. And I will, if I do this calculation, I will get something like 400 terabytes. And I understand that it's not very easy to many people to handle terabytes, so I converted it to movies for you. So it amounts to about 45 years of continuous high definition video. So our cortices can store enormous amounts of information, like your essentially entire experience in 45 years. And so it's, I mean, this is a back of the envelope estimation, but the thing is that there's a logarithm there, which, as we know, is 1/3 power. And, so it's very shallow function. So even if you make a mistake by a factor of 2, it doesn't make much difference. So, excuse me? What? Please feel free to ask questions, by the way. I mean, I understand it's not easy materials. So it's going to get worse. So another thing to like put this in perspective is the amount of information which is present in the genome. Genome contains about 1 gigabyte of information, which is about 5 orders of magnitude less than this number. Just again, in terms of perspective, it's about one hour movie, right? Like high definition video. So it's like 1 hour versus 45 years. But the interesting thing is that the brain cortex is created from the genome, from the information, from the blueprint, which is contained in the genome in the course of neural development. How is this possible? It can be viewed as some form of paradox, and this paradox was discovered many times throughout the years, beginning from 1963 by the guy who actually discovered the modern rules for neurodevelopment. He was a biologist who was actually informed about information theory. And it was also discovered by us at some point. So it's an interesting observation. Like the good news here is that whatever differentiates us from mice or from monkeys, for example, is contained in a short instructional video, which is about 1 hour long, right? So in principle, it's easy to explain, right? It should be easy to understand. So the bad news is that there is some kind of discrepancy here. So how can we create this functioning brain from such a small blueprint? The paradox is, of course, is a little bit contrived because those are different quantities. So what genome contains, it contains something called Kolmogorov complexity. It contains a program, right? So although the information and Kolmogorov complexity are both measured in bits, so those are completely different quantities. You can have a very short program that creates a very complex structure, such as, for example, you could say that this is a network which is set up randomly, right? It requires very little information. But we know that brains are not created randomly. So the idea is that genome contains some kind of instructions which were inferred in the course of evolution, which are really important. And that is what is called genomic bottleneck. And just to illustrate why it's called a bottleneck, there is this picture. So remember that there is this red arrow where the genome is expanded and it creates our brain of a newborn child. But there is also another arrow, which is here blue, which is when the brain is actually imprinted in the genome. It's shrunk back in the genome. And what I mean here is not the evolution, I mean evolution, right? So this arrow is produced by evolution, whereby the most fit brain will be represented in the genome. I don't mean that there is like the information from the brain somehow goes into germline, or there is some kind of Lamarckian evolution. It's just that this blue arrow represents a natural selection. Okay, so the idea here is that in the course of like evolution, brain has undergone millions of cycles of expansion and contraction, expansion and contraction. So each generation represents one of those cycles. And so which is an interesting thing. And the idea is that that's why we call it a bottleneck, right? So each generation, like brain structure is put through a bottleneck, through a narrow information channel. And so one possibility that this bottleneck is just a bug, right? So we have to deal with it somehow. But an interesting hypothesis to pursue, which I'm going to argue for in my talk, that this is actually a feature, because imagine that you need to pack like a bag, but you have only a small bag, but you have to put your entire life's experience into that bag, and like your enormous cortex, all of your memories. So you will probably be very careful about what you are going to put there. So this is a constraint that we argue is important, and therefore the idea is that evolution has shaped the brains in such a way, and it has shaped the genome in such a way that we keep only important features that will generalize, which will help our offspring to survive. Questions?
Yes, probably naive one. Why brain and not, let's say, giraffe's neck or other selection principle that passes on this information?
Well, giraffe's neck is a simple structure. There's not much information there. It's probably like a few bits of information is easy to set up. But yeah, so the idea is that there are a lot of giraffe necks with us, which are stored there, which are, which we want to discover. So there are a lot of simplifying principles that have to be operating in the brain. So it's not just a amorphous network that learns, like in AI, for example, that learns everything. It's shaped in the course of evolution to learn only specific things. Yes?
Is this similar to the idea of a grandmother neuron?
The brain is what?
Is this similar to the idea of a grandmother neuron? Like one maps to like this mesh.
It's not a grandmother neuron because there's still a lot of information there. It's just, yeah, I mean, it's similar, but it's not like there's one neuron. It's like 1 gigabyte of neurons. Like in terms of amount of information that you have in the bottleneck and it's narrowing, there is a lot of information, just not one neuron. But probably a grandmother neuron would be one of those solutions, right? So it's one potential solution. We just want to be able to discover them. So this is the genomic bottleneck hypothesis, is that a genomic bottleneck had led to the distillation. So this process of cycling brain through the bottleneck, the distillation of important information about statistics of the outside world, and to emergence of general intelligence. So it's a hypothesis that we're trying to test. Of course, it's difficult to test evolutionary hypothesis. And so I'm going to try to test it using tools of artificial intelligence that I'm going to describe you in the next half hour or so. So one of the ways how question.
So there's also epigenetics like methylation. Is that also taken
into
account in this 1 gigabyte?
It's a great idea. So of course, there is also epigenetic information which is stored in the cells, which is passed along the offspring, but it's probably less than 1 gigabyte. It enhances it probably by a few %, but it doesn't really resolve the 5 order of magnitude difference. That's what we think. So, of course, like one of the things that how this bottleneck can work is through, for example, creation of the learning rules that will operate in the course of our life. So those learning rules could be simple, but another way is like in many organisms, some behaviors which are some organisms are created, they're already perfectly capable of doing very complex behaviors right after birth, right? And those behaviors must be stored in the genome. And I'll just argue that those behaviors can be very complex. So I'm just listing some of them. Of course, many of us can relate to this baby geniuses, right? And the newborn turtles, which is my favorite example. So the turtles are born in the sand, close to the beach. They wait for the darkness, for the nightfall, because otherwise, if they pop, so you see this turtle is waiting for the sunset. Otherwise, they'll be eaten by the predators, and then they come out from the sand, and then they run to the sound of the seashore. Of course, they have never learned this behavior, right? It's totally imprinted in the genome. So many animals are capable of walking. That's like this newborn deer right after birth. They follow their mother. So like the spiders can make their webs, birds can fly. And another interesting phenomenon is the human capacity for language, which according to Chomsky is some features of it are imprinted in the genome. So that's why it's easy. We can learn languages. So very few examples. So those are some examples. So we decided basically to pursue this hypothesis just using artificial intelligence to see if we can create like an artificial intelligence analog of this genomic bottleneck. But before we do that, I just want to review the general idea of how is it possible? How do the genes, how do they create connections? So what is the mapping between this one-dimensional structure of DNA and the complex topological structure of connectivity in human cortex? And the idea how it was created was hypothesized by this person whom I already mentioned. He proposed the information theoretical hypothesis about bottleneck, the first, Roger Sperry in early 60s. So the idea is this. It's very simple. So I'll just read it. The cells and fibers of the brain must carry some kind of individual identification tags, presumably cytochemical in nature, by which they are distinguished one from another, almost in many regions to the level of a single neuron. So the idea is that neurons will emit some kind of molecules. They will carry and emit a molecule, and the other neuron is capable of smelling that molecule. I'm just translating this sentence to like modern English. and recognize, like follow, grow in the direction of the molecule that they want, and they will avoid molecules they don't want. And by using this kind of cellular sense of smell, they're capable of finding neurons that they want to connect to. So that's the hypothesis. And 30 years have passed since that hypothesis was formulated, and some of the molecules were discovered. And I'm going to give you an example of this system where it's basically the connector that from the eye to the brain. So like an eye, we have about 1 megapixel in the eye. So there's about 1 million fibers that grow out of the eye, and they have to connect somewhere to the brain. So how do they do that? That has been figured out. So this is an example. So this is a cross section through the mouse eye. This is like a pupil, you can see. This is retina, retinal ganglion cells. Those are the connections that grow out. And so this is the surface of the retina. And what is shown here is this density of the protein, which is called FA5, which if you look carefully, it has a gradient. So it's high here, close to the temple, and it's low here, close to the nose. So basically, the horizontal coordinate of the eye is set up by the density of this protein, which is roughly exponential, actually. So the model works like this. So this is in the eye, there is this protein called FA5, and in the target of the eye, which is called superior colliculus. I'm sorry, there is some Latin naming here. There is a ligand for this protein, and the ligand has also this graded expression, and the neurons, they grow out of axons, they grow out of the eye, and they are capable of distributing themselves along this axis of the target of superior colliculus. And I recognize that this is all very complicated, so I just formulated it in terms of electrostatics model. So imagine that this level of this protein is just the charge UA, and the level of this ligand is the electric potential phi A, and you can just like write in Hamiltonian for this interacting system. So this would be a sum over axons of the charge associated with each axon and the potential where this axon terminates, and of course, like all axons, because like this interaction is obviously repulsive, all axons want to be here. They want to slide to the point of minimum potential energy, but that is forbidden because they have there are actually interactions. So there's exclusive repulsion between them, so they cannot occupy the same space, right? So it's actually an interacting system. So I'm not showing here the interaction part of the potential just for simplicity, but the reason why they cannot slide all here is because they repel each other.
There's some chemistry that Does it show?
It's a chemistry, yeah. It's a very funny chemistry. But I mean, I can talk about it for like an hour, but I'm not. So just assume that there is like you know, Misha was describing, there is a repulsion between them. So it's an interacting system. And it's like if you just minimize this Hamiltonian, you will realize that they will distribute themselves along this axis. So the highest charge axons will end up here, and the lowest charge axons end up here. And imagine that you just like minimize this like using some kind of Monte Carlo simulation. So of course, the question that you can ask is what happens to the vertical axis? So how is it? It's only 1D, but how do we do the second dimension? And of course, for the second dimension, there is a second molecule, which is called FB, which is just another charge of a different color, which is distributed like this. And for this charge, there is also another potential called FB. And that's from this layout, you can see there is actually attraction between the FB and FB. And you can just add another part to the Hamiltonian with a minus sign because repulsion.
You're talking here about the optic nerve that goes all the way back,
right?
The optical cortex,
right?
So how is this such a long range thing? So I mean, this is several centimeters,
right? It's not several
centimeters. In humans,
when the brain develops, it's actually a few millimeters. Like it happens when they're very small. So they're next to each other. They're just like they pulled apart later. Right. So this is basically how this connector, like a million wires, grow out of the eye. There are actually 6 targets, so this happens 6 times in the brain, but in a mammalian brain. But the overall idea, I mean, you understand the overall idea is that there is a system of charges and there is a system of potentials, and they're organized, choreographed in a complicated manner that can create a very complex connectivity. Yes.
But then this would give you on average the right connectivity, but obviously not precisely, right? You'll have some bundle of like soldered stuff.
Yeah.
And then presumably the system would have to learn in maybe a few first hours or something to make sense of what they see, right? Somehow.
You're absolutely right. So there are multiple ways. It's hardly that you can make connectivity with a single neuron precision using this strategy. And it's actually designed to be sloppy, so you can accommodate, it can become robust. But there are multiple ways how that problem is solved. Yes. No question.
How does it resolve the information paradox? So this requires only one.
Exactly. So this is actually how this guy, Roger Sperry, why he formulated the information paradox. He said, look, there are only 2 molecules, and they can make million connections. So he actually was a theoretician. Well, he was not a theoretician, he was a neuron anatomist, but he a theoretician at heart. So he figured out that just with 2 molecules, you can create million connections. If you have gradients. So he predicted that there are gradients. He didn't know about them.
How does this create information? I don't understand.
It resolves the information paradox because you can make million connections. So there are million neurons connect to million neurons. And you can do trillion neurons, right, with the same strategy. But you only have 2 molecules, A and B. There are like 2 bits of information, limited amount of information that you need to use.
You have not only 2 molecules, you have gradients who somebody directs, creates.
Right, but the gradient is also
this information. Where is this information?
This information is also easy to create. So, for example, what you can do is you can say, I'm going to look at the neuron at the bottom and multiply the level of this FB by 0.95 and express the protein on this level. And that will create exponential distribution like this. So it's information that doesn't scale with the number of neurons. It's a simple instruction. Yeah, it's not like 1 bit of information, but it's a limited amount.
Because it's very sloppy. If it's sloppy, information is lost, right?
Right. So to answer the question how it's further made more precise, there are multiple tricks. Like you can have on top of those proteins, you can have another proteins which define it more precisely. So once you arrive to the zip code, you can do like more precise, like on the street level navigation, or then find a house. or it can also be involving neural activity, right? You can refine connectivity using neural activity.
I mean, the newborn starts walking sloppily and then immediately learns. So there is some connections that are probably fixed afterwards in some sense.
Right. So
Most of them are fixed after.
so there is like enormous number of
Huge
tricks.
majority.
Right. There's an enormous number of tricks that the system is capable of using, and they all have to fit in within this 1 gigabyte. So we actually have been working on this model. I'm giving you like a very brief snapshot. We've been working on it for about a decade, and it goes back to like this is inspiration from the quantum Hall stripes. Turns out that some analog of quantum Hall stripes exists in the brain, and I'm showing here the picture from macaque monkey primary visual cortex, where you can see the black regions. So this is like a surface of primary visual cortex. The black regions are dominated by the left eye, and the white ones are dominated by the right eye. So there's this kind of zebra skin type pattern which resembles quantum Hall stripes, and we build the condensed matter like theory, which is basically based on the chemical labels that I described that describe this pattern. I'm not going to like basically describe you the details. I mean, if you're interested, you can read the details there. But it was a fun ride, which lasted for about 10 years. But now enter the age of artificial intelligence. That's what I'm going to talk about next. Just to summarize, so the idea is that genome defines molecules, like it generates neurons. The neurons produce thousands of molecules. And also it defines the rules of how different molecules interact. They can be repelled, they can be attracted to each other, and maybe some more complex nonlinear interactions. And that ultimately leads to creation of the cortex, right? So we want to create an AI analog of this and like write a software package and apply it to different like sorts of AI algorithms. And this is how our algorithm works. So imagine that this is your cortical network. We call it phenotypic network. So it's already one that you want to encode in the genome. It's already created. And there is one entry in this like this matrix element ij in this network. So we are going to, for each neuron, for neuron I and for neuron j, we are going to define molecular labels, which are just from some array. It's probably like a 1,000-dimensional array, which defines all the proteins that this neuron can produce. And then we are going to send those proteins to the, we're going to send them to some small network, which we call GNet, which embodies the interactions between those different molecules. And this basically network will mimic the behavior of the genome. So this is generally our approach. And then we're going to use the various types of artificial intelligence tools so we're going to make this work perform at some task. So we'll require it, give it some X and require it to do some behavior, act in a certain way. And then we're going to use this backpropagation algorithm to learn the correct GNet. So it can perform using the input and output relationship. So this is the approach. So computer scientists are very sophisticated people. So they actually developed this idea. They implemented the chain rule of differentiation, and you can compute the gradients. Like for example, you can compute the gradient of performance for this network, for the P network, which is your cortex. And then it will automatically compute the gradient for the GNet that will minimize this performance, that will optimize the performance. So you don't actually need to think about it. So it will happen automatically. But that's the overall idea. And remember those, like the red arrow is the neural development. So the neural development will produce the cortex. And instead of evolution, we're going to use this backpropagation algorithm that will shrink the cortical network into the GNet. So that's the overall approach. I'm going to illustrate it. In the example of this. This is a hydrogen atom for AI tasks, where this is like the handwritten digit recognition data set, where the network is you're supposed to train a network that can recognize digits written by American high school students. And so this is like the neural network. You feed it some image, like just like the pixels of the image, and it's a two-layer network. You know, there are some weight matrices, there are two weight matrices. It's a two-layer network. It actually be trained to recognize. It makes only 2% mistakes. So if you feed it 2, it will tell you 2. But so what we're going to do is we're going to create this network from two networks which are called GNets, which are 300 times smaller than the green one. And we're going to train those networks to generate this network like from birth. And my point is that, so this is the example of performance for the so this is a naive when you just train the network, the green network, to recognize handwritten digits from 0. It starts from 10% performance. Obviously, there are 10 digits, and then it slowly will train to 98%. But this is the one which is created from the GNet, from the blue network, from the genome that we trained. And at birth, it already can work with about 95% performance, despite the fact that it was shrunk by 300 times. So this is an example of bottleneck, right? So you shrunk the green network into the blue network by 300 times. And when you produce the green network from the blue one, it already can act at 95% performance. So it's as if you had some organism which was born, it can already recognize digits without any training. Yeah.
So to make the small GNet, you used an already trained full net?
No. No, it doesn't work actually. So if you just try if you fix the green net, the P net, it's not going to work. So you have to find a very specific P net that is compressible. Question?
How does it compare to just storing, like working out the neural network?
Yeah.
And then storing it with some just extremely lossy compression algorithm, and then starting anew from that?
Yeah, it's not going to work. I mean, with benchmark it, it's not going to work either.
So how do you make the small network? How do you?
This is like literally the structure of it. It's just a fully connected network. It receives for each neuron, it's a pair of neurons. It receives two arrays. In this case, it would be like X and Y. And it's literally, you can compute the number of elements in it, and it will be 300 times smaller than that one. I want to show you, so this is like a very important question, like what is actually going on. So this is like a space of all the networks, of all the PNets. So these are the networks that are high performance, and these are the compressible networks, the ones which you can compress into small genome. And what our algorithm is trying to find, it's trying to find this very small subset of the networks that are both high performance and compressible. So if you just take a random high performance network, you cannot compress it. It will be garbage. So I want to just to illustrate it, to entertain you a little bit, I want to look at the example of walking network. So this is like a physical simulator of something called half cheetah. This is like an organism which is limited, has 6 joints, and it's limited to move only in 2 dimensions. That's why it doesn't topple over, right? So this is a naive cheetah. It's controlled by like a small neural net, like 3 layers, about 300 neurons. So it hops around. It's a naive thing, not do anything. But the idea here is to train it to walk forward, right? So it's a typical. So this is a naive cheetah, and this is one which is trained to walk forward at the highest possible speed.
How you train it? I mean, what do you mean by training?
You train it to move forward at using some kind of algorithm which is called reinforcement learning. So you reward it for going forward at the highest speed.
Okay.
And this is the best you can learn. So it looks like it discovers this very weird solution, which is called reward hacking. So it chooses to walk on its chin for some reason. But like in 80% of cases, you will find that those solutions they have some kind of reward hacking. It will either like slide on its back or do something weird. And this is the cheetah so this is the cheetah which is trained using our algorithm. It's about 5-fold compression. And in most cases, I think in 95% of cases, so this is a newborn cheetah, which is created from a smaller network, from a smaller genome. And it actually performs almost as an adult. You can see that goes off the field a little bit later, but it moves almost at the same speed as well. So essentially, the organisms that can walk immediately after its birth. But the interesting thing, so what if we now put the two cheetahs into high gravity environment? So we put those two organisms in a novel environment. See if those other solutions will generalize. So this is the cheetah which was trained without the genomic bottleneck. So it learned this reward hacked algorithm. So it's going nowhere. And our cheetah, it can still look in Jupiter in case of gravity enhanced by about 50%. It can still move. It looks a bit sloppy. I call it Jupiter shuffle, but it still works. So it just shows you that the compression of neural nets allows them to find solutions that can generalize across environments for some reason. We also show like more examples of this, which are very boring in our paper. I would like to talk about interesting thing, which I mentioned Newtons. I want to basically talk about how this may apply to physics. So this is like very conceptual and philosophical. So I learned from this book, Culture in the Course of Human Evolution, this idea that brains and culture, they co-evolve.
They do what?
They co-evolve, they form a niche. They evolve together. Human culture and brain, they evolve together, or in terms of that book, they form a niche, which means they kind of form like a negative imprints of each other. So one example would be the Chklovskii hypothesis that the structure of natural language is somehow imprinted in the cortex. Another example is my favorite example is the acquisition of controlled use of fire. You know that when our brain consumes about 17 watts of energy, about 4 of those watts, they come because we cook food. The cooking gives us extra, cooking took energy from the gut and gave it to the brain. So just by being able to control fire, we expanded our brain capacity by about 25%. So that's an enormous impact of culture on our cortical architecture, right? So arguably, Prometheus, when he gave us fire, he gave us 25% of our brain capacity. So this is important. So the question is if cultural phenomena can also form bottlenecks. I was talking about bottleneck in the brain, right? But I think like one interesting example is physics. So physics is condensing the behavior of the natural phenomenon, very, very compact rules, which can be described by equations and calculus, right? So, and the reason why this happens, like one of the reasons why this happens is because it's easy to teach, right? So you can teach people in like 12, 20 years, the entire content of our physics. So it's a way to pass this information from generation to generation. So this is an example, physics is an example of cultural bottleneck, right? So this is what this
science
department is. Any science which strives to find a reduced description of things, right? Simplified description of things. And in fact, like the job of many theoretical physicists is actually to simplify things to the bare bone so that they can understand things, right? That's what anyway, so.
What about misconceptions? I mean, also,
excuse me?
If you can some misconception, they also can pass through generations. So I'm not sure why it's about science rather than.
It's also a bottleneck, right? So it's another example of bottleneck. Delusions.
Any theory.
Delusion.
No, they're not science, not theory.
Theories, yes. Yeah, as long as it's just
bad theory, good theory, anything. Religious.
Yes. Okay. Yeah.
I want to describe. I want to just notice that those two things, those two streams of information, like the brain, the cortex, and the culture, can be viewed as self-replicating quantities. And the definition of self-replicating quantity is that if you wipe it out, it's not going to recover. Like if you, for example, forget the language, it's not going to recover. Right. So the other stream of information genome cannot help you recover English language if it's lost. Or if, for example, some species lost, some cortical architecture, wonderful, 5 minutes. If cortical architecture of some species is lost, there's no cultural phenomenon that can reconstruct, right? So each of those streams are actually independent self-replicating quantity or entity. There is another self-replicating entity which is emerging, which is tools. So tools are also self-replicating. You, for example, you cannot assemble a shuttle without a screwdriver, right? So if we lose all the tools, we will not be able to produce more sophisticated tools, right? So from that definition, the tools are becoming more and more complicated in the course of evolution, and they're co-evolving with everything. And I put here this modern GPU A100, which is also a form of tool, right? So, and tools should be added to this system of niches. So they also form a niche between culture and brain, right? So the point that I want to end this talk with is this, that in this triad of brain, culture, and tools, one can be easily gone missing, such as the brain. So those things can just continue self-replicating, to the future. So as a conclusion, I hope I argued to you that information about available in the genome is not sufficient to set up cortical connectivity with a single neuron precision. So evolution has to have discovered some set of methods of how to compress the brain architecture, some tricks. And we built AI tools that can help discover those tricks using just data sets, like large data sets that are available in AI. And and genomic bottleneck can help placing cortex through this genomic bottleneck and help force evolution to discover architectures which can generalize across environments and potentially lead to evolution of general intelligence. So I would like to thank my collaborators here and the funding, and you for your attention. Thank you.
Interesting. Questions?
Yeah.
Is there a reason why one cannot transfer the whole brain from generation to generation, and you have to first shrink it to a genome and then?
Well, this is how biology exists, right? So we go through single cell organisms to produce the offspring, and you can argue that it's a bug. I'm just saying that it's a feature. It actually helps us to become smarter. So that's the argument.
Yeah.
So you said that only some small fraction of possible architectures have the property that they can be compressed, right?
Yes.
And you have some ways to cycle through various architectures to find those.
Yeah.
Okay, once you find them, what have you discovered? Is there certain properties of those?
Oh yeah. It's fascinating. So like in that simple, and this is like a wonderful question. So our algorithm finds the architecture, but how does it compress? So it turns out that in this simple digit recognition algorithm, right? So if you don't involve bottleneck, the network will just remember the digits. So it will contain the weights in the network will just contain like masks corresponding to the digits. So if you start compressing it, it discovers the Fourier transform. So the first layer of the network will do some analog, will do Gabor transform, like a local Fourier transform, because the digits are kind of translationary. You have to recognize them in different points. And then the next layer will learn how to deal with the Fourier transform image. So this is fascinating. You have to actually do neuroscience on those networks that we'll discover, and we're only scratching the surface of it.
So you're talking about the connections and the spatial architecture, but the information also exists in time. It's the timing. You'll have neurons that are all firing, and then suddenly they'll form a coherent oscillation.
Right.
Will then disappear. And so that part also, I don't know, would that part be part of the culture? Because that's something that you could have you could know all of the connections, like knowing a map of every road in the United States still won't tell you how long it'll take to get from one point to the other because there's traffic and other issues.
Yeah. Absolutely. But again, we're only scratching the surface of it. And the simple organism, the half cheetah, it does actually process information in time, but we don't know how it does it. So it is somewhere hidden in the network, and we need to do neuroscience. But I agree with you. Like the way how brain deals with time is very complicated. It has a recurrent neural network, which has intrinsic time scale, multiple intrinsic time scales, and that's how it can do it. And so it's too early for us to really see how it's going to work out in if we try to bottleneck some arbitrary recurrent neural network.
Okay,
thank you.
Okay, thank you. All right.
Okay, great. So next up it's today here by Chklovskii of Science Foundation and NYU. That's also something about neurons.
Right again. Work during the break. So this is my son put this up for me because I tell him to focus all the time if he wants to get back at me. Okay. So when I transitioned from physics to neuroscience, I realized that being in different field than your dad has its advantages and disadvantages. And the advantage is nobody asks you why you spell your name different from your dad's name. But the disadvantage is that nobody knows how to pronounce my last name. So I had to make do with this pictograms to help people along. So I think we're living in a very exciting time. As you already heard from Alex, artificial intelligence is taking over, and this is unprecedented, and I'm a huge fan and avid user of ChatGPT. But we should also recognize that this new technology has its limitations. And so, for example, there was this case about a year ago that lawyers prepared a brief using ChatGPT, and the judge found out that they're citing some cases that were totally made up. They looked like real cases, but actually ChatGPT hallucinated them up. So in this case, they just ended up with a fine. But there could be worse scenarios when you have a self-driving car. And in general, the discussion in this tech companies is not really about this now mundane applications, but actually can AI become AGI, which is poorly defined term meaning artificial general intelligence, roughly equivalent to the human brain. And I don't believe that it's possible with the current architecture, but some people think they can get there just by scaling up the current networks. But even if that was possible, the energy consumption grows very fast. And if it continues this way, we will spend the whole energy budget of Earth to train next GPT, whatever, 10. All right. So there are a lot of problems with the current AI approach.
But train on what? I mean, you have to also have it.
So they apparently used all the text, available text for training, but no one figured out how to use videos.
I see. So you can pixelate.
So you could start using videos, okay? So there are a lot of problems with AI, because it's behaving in this non-human way. But what if I told you that there is an alternative architecture that, where hallucinations can be controlled, it doesn't make mistakes which are natural for human, and consumes less than 20 watts, okay?
And each of you is, of course, in possession of this architecture. But you would say, well, wait a second. But we're in this artificial neural networks that underlie the AI revolution inspired by the brain as well. That is true, they were, but that was 70 years ago. So this is the basic foundational unit that has been invented in the 40s and 50s and 60s of the last century, inspired by the brain. And it's just like a weighted summation of inputs passed through nonlinearity. It was an incredible achievement, of course, a pioneering work, but it's terribly out of date now. Over the last 60 years, neuroscience moved ahead, and we know for a fact that this is a rudimentary cartoon of a biological neuron, not an adequate representation at all. And I'm not talking about reproducing some biological details like biophysics of ion channels or gene expression, things like that. This model does not capture the algorithmic complexity of real biological neurons. Yet, all the AI that we have now is built on these foundational units. So our goal is to go back to the brain and come up with a revised, smarter neuron unit to build better AI systems. Okay? So to be specific, what are the two? So here are the two main distinctions that I'm going to focus on today. One is that McCulloch-Pitts neuron is a feed-forward device. Information just flows from left to right. And second, that it has an instantaneous response. Just whatever comes in at a given moment determines its output. And that's not at all like how the brain is wired. First of all, neurons are feedback devices largely, and they have very sophisticated and interesting temporal dynamics. Okay? So just to back up the first point that the brain has neurons are in feedback loops. This is so-called the connectome, the graph showing all the neurons in this little worm, C. elegans, and connections between them. Okay, and that was something that has been reconstructed just over 10 years ago. And if you analyze that graph, you will find out that 80% of neurons belong to cycles of varying length, but you can always find a way from the output of a given neuron back to the input to that neuron. And it's also true for the majority of neurons in our brain and in the brains of most animals. So the output of the neuron can, in fact, affect its input. And this is leads me to sort of the central summary slide. So if you feel sleepy after lunch, you can just go to sleep after this slide. Basically, what we are proposing is to replace the McCulloch-Pitts model, which we argue is a rudimentary cartoon of what the real neuron does, with a more sophisticated, smarter neuron. And because it's part of a feedback loop with other neurons in the rest of the world, the correct way to analyze its function is through the methods of control theory. And that's why I call it a feedback controller. And what the novelty here is that the neuron actually doesn't just process its inputs and produces outputs. It actually is monitoring its inputs to learn about the effects of its outputs on the rest of the world. And it has some objective trying to drive the rest of the world to some particular state. And it's monitoring its state through its inputs, and that's how it goes along its function. So in my talk, I will have two parts. In the first part, I will give you a proof of principle that neurons can actually do it. Your actual biological neurons can do this, can perform such a sophisticated task, much more complicated than just a feed-forward summator. And in the second part, I will talk a little bit how spiking neurons are going to do it. So for the first part, I will consider neurons that don't spike, like Alex told you, but they produce a continuous output, which is analog output called graded potential neurons or fine rate neurons. Okay, any questions so far?
What is the K feedback?
So whenever you have a system like this, which has a higher dimensional dynamics than the observation dimensionality, is a partial observed system, and you cannot reconstruct its state based on instantaneous observation. So you have to monitor the system for a little bit to know what the latent state is. So so-called time delay embedding, it's used in nonlinear dynamical systems. And it has to take into account that the state of the world doesn't just evolve by itself, but is also affected by its own output. So you need to know about its own output to predict the state. So it kind of has to know about its own impact on the world. So for example, you know this fact perhaps that no one can tickle themselves. Okay, if you try to tickle yourselves, you cannot do that. You have to have another person tickle you, then it works. The reason is that there are loops in your brain that tell you to expect the tickle. And if you expect the tickle, it doesn't feel ticklish. Okay, so that's an example of such a self loop on a bigger level. But what we're arguing that each individual neuron has a loop like that. Okay. Yeah.
But what if the neuron, like the output of that neuron actually has little impact on the environment? For instance, so here, are you assuming that what if like a neuron does not have any impact on the environment, meaning that it will output something, but it will actually won't change anything, so it will keep training into
Okay, so the question is, what if a neuron doesn't have any impact on the environment whatsoever? Then evolution would get rid of such a neuron, okay? Because it's pointless. But to restate your question, but the question is very good, okay? What if that impact on the environment happens in a long time scale so that the neuron cannot associate it with its particular output, right? And that's true, for example, for the neurons in your eye, in the retina, okay? They produce a spike and, you know, the eye moves around. So eventually it will somehow influence what they get, but it's hard to imagine that they could use that information. So I have a slide to answer that question. Can you please repeat it in the end of the talk, because then I'll put up the slide and answer it, okay?
Thank you.
It's a very good question. Any other questions? Okay. So, what we're proposing is this, that the neuron is this feedback controller, and no one has proposed it before, even though people thought of the brain as a whole as a controller. And the reason is because people thought that it's a very complex thing to do. And so what I'm going to try to show you next, that this can actually be done with the means that are at the disposal of biological neuron. And all it needs to do is something called direct data-driven control. And I'll explain what it is. So, okay, let's do some work now. Let's consider the simplest possible dynamics of the environment, which is just a scalar variable x. And in discrete time, there is an evolution xt plus 1 equals a times xt, and a is greater than 1. Some kind of factor that is greater than 1 that makes this dynamics unstable. Of course, if you have the system that is unstable, it's not a good thing to have an unstable system. And so the goal of the neuron is to compensate for that by suppressing the instability through its control variable u and coefficient b. And the question is, what kind of control law, expressed here as just a proportionality law with unknown w, would stabilize this system? Okay, so without b, this will blow up because a is greater than 1. What kind of w do you need to stabilize this system? So this is like control theory 101. And for a system this simple, scalar, fully observed. Well, we can do this in one step, okay, by bringing xt plus 1 to 0 for any xt. How do you do that? Well, let's plug in this expression for ut in here, okay? And then we have a plus bw times xt, and our goal is to get xt plus 1 to 0 for any xt. That means that the bracket has to be 0, and that means, if I can operate this.
So 1.
Okay. Then what you need to do is to have w, which is minus a over b, then this cancels, the bracket is 0, then for any xt, you get back to 0 in one step. So simple, okay, and you learn it in sort of first week of a control theory course. But can a neuron do this? That's our question. Can a neuron do this? And why wouldn't it? Well, because a neuron doesn't know A and B. It doesn't know the dynamics of the environment. Nobody told it. And it could be changing over time. So A and B could change from moment to moment. So how would it know what the correct control is? And the question is, okay, if it doesn't know A and B, how would it even be able to compute them and so on? So that's what this direct data-driven control framework that was developed about 20 years ago does for you. And I'll try to illustrate it with a super simple example, but it's actually works for any dimensions of X for systems with noise and for somewhat nonlinear dynamics. I'm just illustrating this for simplicity. Okay, so what you do to get rid of this dependence on A and B, the idea is to use the previous experience of the neuron. The idea is that over time, over some period of time, A and B stayed constant. Neuron doesn't know what A and B are, but they're constant. That's all it has to know. And then it has seen throughout that recent history that the state x2 was A times the state x1, and the neuron contributed u1. So it measured or produced all these values x2, x1, u1, and that happened several times. So the recent history of the neuron is recorded here. And the assumption here is that A, B are constant. Then what you can do, you can exclude A and B from this system of equations and figure out how to produce the optimal U without operating in terms of A and B, purely in terms of the past trajectories, including X and U. Okay, so that's why it's called direct data-driven control, right? So you use that data, X and U, and you map X directly onto U without forming the model of the world. Okay, is that clear?
So you don't solve it for A and B, but
yes, you directly solve for the optimal U. So for example, in this case, you want, xt plus 1 to be 0. So what you do, you want to find coefficients G so that you can multiply each equation by its own coefficient and then add them up. Okay, and of course this is true because these are equations and I just added them up. Okay, but now we set those coefficients G so that they satisfy these two equations. This is our desideratum, so we want to set it to 0, then this sum has to be 0. This is our measurement, xt. So G has to be chosen to satisfy this equation. So G is our tuning parameter that we tune to satisfy these two equations. When we satisfy these two equations, we plug in that same G into the expression for U, and that is the U by definition that will solve the dynamics and give you xt plus 1 that you want for the observation xt. That's the basic idea.
That assumes that you don't know A and B, but you know the form of the equation.
Yeah, so the idea is that, of course, the true dynamics is nonlinear. And so what we're relying here is that it has a locally linear expansion. So that for a short period of time, it has to be long enough to assemble those equations. In this case, you just need 2 to solve this. For high dimensional system, you need more. But for a short period of time, you make an assumption of local linear dynamics and you compute the output in terms of the data without referring to A and B.
When we say short, what is time scale? What sets the time scale?
So that depends. So in the brain, this is happening on all time scales from milliseconds to years, perhaps. So the examples I'll show will be tens of milliseconds.
Do we need chemistry or it's just a model like?
So yeah, so I will not appeal to chemistry, but the question will be how are those factors implemented in the neuron, and it will become very, very simple so that you wouldn't be you wouldn't feel like it's too much to ask for a neuron or from a neuron or a synapse. Okay, so at this point it's a very good question because okay, so I said okay, we're going to do it with a biological neuron, but so what? Is that biological neuron going to store all this past trajectories, all this data X and U? Where is it going to store it? And then will it compute these G's at every time step? Okay, that sounds crazy. That can't possibly be represented in a neuron, let alone computed. But look at this problem. This is the problem that we need to solve. Okay, so we need to find G's that satisfy these two equations. These are linear equations. So we can solve them by pseudo-inverse, just like in linear regression, least squares. Okay, so there is a solution for G that we can write down analytically in terms of x's, and then plug that solution in this expression. And when all is said and done, for this very simple, this is particularly simple case when you want xt plus 1 to become 0, when all is said and done, the expression is amazingly simple. The control law relies on the synaptic weight W, which has two terms that are the sums that are basically covariances of the activity of the presynaptic neuron X and the postsynaptic neuron U. And this one is when the activity U follows causally from X, and this one when the activity U is anti-causal, so that activity U precedes X. So these are the two correlation functions that add up with the minus to give you the synaptic weight. And that just came out of the pseudo-inverse of solving that linear equations for the minimum norm of G. So no, we don't need to store past histories, X and U. We don't need to recompute G's at every step. What you do at every step, you update these sums. And they only update it when there is a coincidence or that the presynaptic activity precedes postsynaptic or the postsynaptic activity precedes presynaptic. Okay?
And this W is supposed to be time independent or?
And W gets updated over time.
Yeah, but slowly, right? So.
But slower, exactly.
Yeah.
Exactly. So this is a simple result that comes out of this very basic model. But the reason it's worth putting up is because this directly maps onto a synaptic learning rule, like the ones that Alex mentioned, that was discovered experimentally and serendipitously in the 1990s. And this is like experimental data here from a synapse, and the synapse gets stronger when the presynaptic activity X preceded U, and synapse gets weaker when the presynaptic activity X followed U. And this is just the time difference between the activity of the pre and post synapse. Of course, I'm not reproducing this whole exponential curves. I'm only getting you this switch in the sign and the smaller amplitude here, and beta is related to the covariance between x's. So that's the only thing we're explaining. But look, this simple model doesn't have dynamics sophisticated enough to explain those temporal behaviors. So there's no way we could get this. But we're already getting this switching in time. And what's particularly pleasing is that we can explain this anti-causal part of the learning rule. Why is it that the synapse should get weaker when the presynaptic activity follows postsynaptic? It was a mystery before. But once you have a feedback loop, okay, it stops being anti-causal, so that this neuron produces a spike, and then the spike travels through the environment, and the neuron monitors the environment to know the result of its attempted control to shut down the system. And if it gets something in return, that means that there needs to be a correction in the learning rule, and that's why we have this term, and that's why this part of the experimental plot exists. So this already helps to eliminate a lot in the experiments. Any questions?
How does it apply to the eye neuron you mentioned? You see something, but then there is no immediate feedback.
Right. So we'll get to the eye. I'll show you that in the end.
So it's for
Yeah.
some other neurons.
Yes. So for the eye neuron, it's actually not clear that you have this learning rule. These learning rules were recorded deep in the brain for all the neurons that have loops. So I actually don't know for the eye.
So this is for what kind of neuron? Like
It's like most of the neurons deep in your brain, like in the cortex. Okay. All right. Okay. So we've got this learning rule for W. Okay. And we claim that we don't have to collect data first, but we can update the synaptic weight on the fly for the streaming data as time goes along. So we can simulate this system and see how well it works with this learning rule. And that's what we did. So here's a result of simulation. Here I'm showing you the state X. In the beginning, it deviated from 0. And so we collected the data from the first 4 steps. And we learned the correct W that is shown here in a dashed line. And the colored lines are individual instances of the simulation. And as you can see, it works really well initially. X is 0 and W is optimal. But then we decided to check if this algorithm works when the dynamics of the environment changes, when A and B move around. Okay, will this algorithm be able to track A and B as they change? And it turns out that it doesn't do that. Okay, so we switched A and B, and so the optimal W is now here, but nothing happened because the neuron didn't know about it because X was 0. So 0 is always 0. So it was generating 0 control for 0 observation. It didn't even know that the optimal W changed. We changed it abruptly, but it still doesn't know because by that time X is 0. So just seeing 0, it produces 0 output and doesn't know. To make it suffer, we gave it a kick, right? A perturbation in X, and watched if it would recover. And it didn't really do a good job of recovering. It even went unstable at some point for some instances, okay, of the simulation. And that's because W was not optimal. So why didn't it use the learning rule to learn optimal W? And here is the explanation, okay? So it turns out that when W is fixed, at either optimal or any other fixed value of W, this algorithm breaks down because it doesn't anymore get information about A and B. And to see this, I rewrote this equation that describes past instances. But now remember that W is fixed, and we plug it in here, and this is a constant. Okay? Then we can take this constant out again, and then you can see that A plus BW are together. And no matter what kind of data xk plus 1 I have, I will not be able to differentiate between A and B. And that happened because we have a constant control law. So even though this algorithm kind of works, with any kind of constancy, it fails. So how can we fix it? We added noise. Okay, so if you add a little bit of noise to the control law, then the algorithm works just great, right? It notices that we changed A and B and adjusted W to the optimal value, and then we gave it a kick. It corrected very quickly with very little cost, unlike what we had with the noiseless case. So this is a very interesting result because we're saying that noise in the brain is not a feature but a bug. And in fact, there are not a bug but a feature. Thank you. Not a bug but a feature. And why is it interesting is because the brain is full of noise. Anywhere you look in the brain, there is noise. Even in the level of individual synapse, you might think that this weight describes how the each spike gets magnified as it passes through the synapse. That's true. But most spikes don't even make it across. They arrive at the presynaptic terminal, and only 10% of them make it across the synapse, stochastically, randomly. And we think that this is one of the mechanisms that could provide this noise. One could say, well, but that's just because synapse is too small. It's stochastic because of closeness to KT, of energies closest to KT. But there are other examples in the brain, in addition to the synapse one, which show that the noise in the brain is generated intentionally. Remember that little worm, C. elegans, the connectome of which I showed you? It has a specific neuron whose job is solely to inject the noise in the circuit. If you turn it off, the system malfunctions because the noise does not really help. Same exists in songbirds. They need constant generation of noise to learn the song of their father, which is what they do in development. And of course, you know, for escape, when you're trying to catch a fly, it gets away, it does so stochastically. It adds noise to a decision. Otherwise, you could you could figure out where it goes and catch it. So we think that's a really nice, in this case, it's a nice rationalization why noise exists. But it adds to the experimental evidence that maybe the feedback controller view that we're proposing has some weight because it accounts for this experimental observations.
So nice question, but if the feedback looks at you, I mean, you had some sum over n from 1 to t.
Yeah.
But if you constrain summation up to t, but not from 1, but from t minus delta t.
Yeah.
Does it still not working or?
Yeah, so excellent question. So the question is, what if we don't integrate the sum from the beginning of time, but we actually have a forgetting term, and we just keep forgetting a little bit from the old past in the favor of the recent past. Right. That's exactly what was done in this simulation. And that's, even with that, it failed because of that constancy problem.
That's it.
Okay. But with noise, it survived. But that's exactly the algorithm we actually ran here. Okay. I just didn't want to complicate things. Okay. Okay. All right. So that's all I want to say to show as a proof of principle that, you know, neurons can actually implement the feedback controllers because there are just two sums that define synaptic ways. So someone asked about chemistry. It's very easy. So synapse is a very complicated machine. It involves hundreds of different protein species, okay, for each of which can have different numbers of molecules. And so storing two scalars, which would be the two terms in this correlation, and updating them when coincidences of spikes happen is very easy to imagine, and there are obvious candidates to do that. So that's very easy to do. And that's why we say it's a biologically plausible way. But what's not biologically plausible is that, remember when we looked at the algorithm, I had this discrete time dynamics with the world, and then the control law was proportional. So as if the neuron has to produce the output at every time point. But although there are neurons like that, many neurons have to be, when you look at them, they're spiking. And what that means, they produce the signal which lasts only a millisecond, where the time interval between them can be tens, hundreds, or thousands of milliseconds. So it's a very sparse output of a neuron. So most of the neuron, all the time, the neuron is silent. It cannot produce proportional control during that time. Okay? But the input is coming in. So in this experiment, they simulated the behavior of a neuron by bypassing the synapses, injecting the current directly into the cell body, into the soma. And this was the current as a function of time. And every time they injected that same current trace, they got exactly the same spike trace. So the neuron is an extremely precise machine, despite being close to, all the energies being close to KT. It overcomes this thermal entropy and very exactly produces the spikes. And so if we're using, if we are saying that these spikes are outputs of a controller, maybe we will be able to see the instability of the environment in the interval just before the spikes, right? So then the spikes would be integrated in the signal that the environment is unstable, and the spike would be a control signal producing, stabilizing the world, okay? The reason I'm emphasizing it is in the proportional control neuron, it would cover up the instability. And so we wouldn't be able to check if that is really true, the story that I'm selling to you now, okay? But with a spiking neuron, we would have an opportunity to detect those instabilities in the world right before it spikes. And so then I'm arguing that right before the spike, there should be an exponential increase in the current. Is that really the case? So what they did in this experiment, they looked at what kind of current trace preceded each spike. And to do that, they just summed up the windows before each spike, and that sum produced curves like this. So the spike happened here, and right before it, the current went up abruptly. So it looks like an instability. But what they also found is that depending on the signal-to-noise ratio in this current that is being injected, the shape of that sum, of that linear response filter of a neuron changed. And what we are trying to argue, that change does indeed correspond to a device that would detect the most unstable mode, the fastest growing exponential in the input, and try to filter it out of this mess.
Different curves are, 3 curves are different currents.
Yeah, so there's a different signal to noise ratio, so the magnitude of this versus the noise, okay? So then you get the change in the shape of those things. And then I want to show you, if I still have time.
Yeah, 7 minutes.
Oh, okay. So what
7 minutes to the very end.
Okay. What I want to show you is that if you want to compute the optimal linear filter that would detect a growing exponential, you would get this kind of shapes, and they would adapt with the signal to noise ratio. Okay, so this is the mathematical formulation of the problem. You have, as a function of time, you have this time series that you observe, but you know that it's made out of this growing exponential, decaying exponential, and some noise. So imagine, like in the time of COVID, you get these reports from the field that say how many patients tested positive, and you plot them over time. But what you want to find out is if there is a different variant of the virus that the new wave is starting, right? So these are the old waves, they're decaying, and then the new wave of COVID is rising up. Can you detect it as early as possible from just the cumulative count of all the infection cases? So that's how we model the input to a neuron, by this exponential modes. And the question is, what is the optimal linear filter that would extract this fastest growing exponential, which would be a trigger for control to stabilize, to institute a lockdown to shut down that new wave? So the way to solve this problem is, of course, we can write down the sum of exponential this way, plus noise. And the easiest way, perhaps, to explain how it works is to do the procedure called time delay embedding, where we view this as an output, scalar output of the vector dynamics of this is so-called time delay embedding, where you take a window of recent states and you evolve them over time, where you shift the time by 1, and A is the evolution matrix. Okay? So think of some kind of a statistical process, and this is some linear operator that advances your state. Of course, most of the x's just get inherited from the past, and then you produce the new one as a linear combination, like in an autoregressive process, plus there is noise. So to find the optimal filter, what you need to know is that there is an eigen decomposition of this evolution operator A, and because it's unlikely to be normal, the left eigenvectors are different from the right eigenvectors. Okay, that's unusual. As a physicist, it took me some time to realize that not all matrices, and actually most matrices, are not normal, and so they don't have a full set of orthogonal eigenvectors. And so that's what usually happens in dynamics. So these W's and V's are different, but they're still biorthogonal. So all the left eigenvectors, W, are orthogonal to all the right eigenvectors, except for its own, when I and J are the same. So then the optimal linear filter that extracts the highest exponent is simply the left eigenvector W, 1, corresponding to the highest eigenvalue. That's the solution, because it will be orthogonal to all the other modes, and it will filter them out and leave only the growing exponential. And this, in fact, accounts for the change in the shape of neuronal filter, because depending on how many decaying exponentials you have and how big the noise is, the optimal linear filter goes from an exponential, obviously, if you just have one growing exponential plus noise, you just extract it. But that doesn't work when you have a decaying exponential, because this filter is not orthogonal to a decaying exponential. So you need to modify it because, right, because this is not orthogonal. So the top left eigenvector has to cross zero. It has to be biphasic to be orthogonal to this decaying mode to filter it out. That's how you get this biphasic curve. If there are two decaying exponentials, you have a triphasic curve because you have to be orthogonal to two decaying exponentials and just keep out the fastest growing one. And that's the result of the symbolic calculation with different levels of noise. You see that you're going from this almost exponential decaying curve to the one with 2 oscillations to the one with 3 oscillations, just like is seen in the experiment. So this provides yet another experimental validation of our view that neurons act as feedback controllers. The first was the learning rule, and then there was the ubiquity of noise, and now there is this adaptation of spike triggered average. And that leads me to the conclusion that we think we have some evidence to argue that a neuron acts as a feedback controller that senses instabilities in the environment and responds to them with spiking. I want to thank the people who were involved in this work. Very grateful for their contributions, and I'm ready to take questions, but there was already one question outstanding, which is what happens to neurons that don't have an immediate feedback loop. Okay, so let me do that first. Let's see. Oops. Okay, so what about these neurons that do not have a loop that immediately closes them, and so they cannot be using their output, their input as an immediate information or learning signal to adjust its outputs, right? What I do have to assume is that the whole brain is still in a loop, right? Because if these neurons, we call them sensor neurons, do not affect the output, then they wouldn't be there. By evolution would get rid. So they feed information to downstream neurons that actually implement control. That's all I need to assume. But there doesn't need to be a feedback loop right on that neuron. It turns out that there is this amazing thing called data rate theorems in control theory, and tells you that if the information rate in this links is not infinite, but it's limited by information capacity, then each such controller can stabilize only those plants whose eigenvalues, lambda, non-negative eigenvalues, do not exceed the information capacity of the links. Okay, think of Kolmogorov-Sinai entropy in nonlinear dynamics, right? That if you measured the state and then over time it exponential grows, so the uncertainty grows exponentially. If you take the log to compute the entropy, then it grows linearly with time, and the coefficient is exactly that value. Okay, and so basically, you have to have that communication by this sensor to have high enough information capacity for the controller to be able to stabilize the system. So you don't need to require each neuron to be a controller, but that neuron has to respond to instabilities without too much delay, because if it doesn't, then you lose the observability. The rest of the brain decouples from the world and you cannot control it anymore. Okay, so just requiring this kind of information rate will tell you that neurons should be responding even if their spikes are not immediately controlling the world, but even if they're just informing the brain downstream how to control the world. That's why everything what I described applies to all the neurons, not just the ones that are embedded in the immediate feedback loops.
Yes, there was another question that reminded about your question.
Yeah, I think that's what was addressed.
Yes.
Yes.
Okay, so then.
Sorry if I already asked that question before. So it just suggests that neurons are controllers, just controlling, right? But they must be doing something useful other than controlling. Like, what could be the difference in visual and auditory neuron? Some neuron that control action. Looks like your theory applies to every neuron. So what differentiates different neurons responsible for different tasks?
Well, so we think that, although all neurons are controllers, they may have different objectives of control. What those objectives are, we really don't know at this point. The only thing we used is that the loop has to be stable, right? Once you have a closed loop, it cannot be unstable. And that's the only part of the objective we use. But just stability is not enough, of course, right? Like you also need to live, right? Like the easiest way to stability, you just go to sleep, shut down all the activity, right? So that's obviously an important part of the objective, but not all of it, right? So there must be some other objectives, like these neurons must keep signaling about the instability, right? And we don't yet know how to quantify that. And we think that different classes of neurons have different parts of the objective that they are trying to achieve. And then the big question, sort of the million-dollar question is, if each neuron thinks of itself as a controller of the rest of the network, how do you put together all those controllers and they still perform some coherent action? And that we don't know, and that's why we have to use ChatGPT and not something based on natural intelligence.
More questions? Yes, please.
When you mentioned the filter, as a right eigenmode of the dynamic system matrix, those right eigenmodes are not orthogonal to each other if the matrix is not Hermitian.
Exactly.
Then would it possible that when you add noise, that optimal right eigenmode was perturbed to another eigenmode because they are not orthogonal? Then it doesn't do the optimal job.
So I'm not sure I completely understood your question. So in fact, you correctly pointed out that because the evolution operator is not normal, then the eigenvectors, the right eigenvectors are not orthogonal to each other. But they're biorthogonal, so that the left eigenvectors are orthogonal to the correspond to all the other right eigenvectors except for its own.
I understand this part. But
Okay, so what's the question?
if you add noise that such that the system choose instead of this optimal eigenmode, which corresponding to the largest eigenvalue, some other eigenmodes, but they are quite close to each other in the vector space, but it corresponds to a very different eigenvalues. Is it possible?
Are you referring to the fact that a non-normal matrix would be eigendecomposition of a non-normal matrix is very sensitive to small contributions of noise?
I'm not sure about this part. Yeah, that's my question.
Yeah, so that is a little bit of a problem here, and I now think more in terms of the singular vectors here, which are better, more robust. But the results are very similar.
Okay, here's further questions. Let's take it again.
Tomorrow we start 8:30.
Next morning. We are not today.
10 minutes before. Very quick.
But I don't know what exactly. So, I already asked Svetlana to discuss this.